Okay, good morning, everyone, for joining for day two, Cyber Resilience and Operational Dominance Summit for Critical Infrastructure. And we had a good turnout yesterday, and hopefully we are also seeing more people tuning in for this day. In day two, focus on industry challenges, and so we have a great keynote talk coming, and then there is a good industry panel. And there is vendor perspective from an OT side session from Andrew Ginter. And then you have a nice cyber-informed engineering workshop that's going to have more students attending. INL is leading that workshop. And with that said, here is the schedule for day two. So in the event, if you want to catch some sessions, depending on, I know everybody's busy on different things, but here's the event schedule look like. And we also have a luncheon talk on OT and ICS cybersecurity training by Jeff Hahn from INL. He has also graciously agreed to do this webinar for us. Ginger, I turn it to you to say some words.
Thank you very much. Today is a day that we shift from research and kind of admiring the challenges to digging into how we will mitigate them. And we start today with a presentation from Dr. George Shea. She is the Chief Technologist at the Foundation for Defense of Democracies, where she leads the Transformative Cyber Innovation Lab. With over 30 years of experience across federal, defense, and commercial sectors, she has authored influential policies on software supply chain security, quantum resilience, and national risk management. Her work has shaped Department of Defense acquisition strategies and informed congressional briefings on critical infrastructure security. A frequent global speaker and former member of the President's Council of Advisors on Science and Technology Cyber Physical Systems Working Group, Dr. Shea continues to drive innovation in cyber resilient design and operational resilience. And her talk this morning is current challenges for critical infrastructure security, policy, regulation, and technology. Dr. Shea, thank you for joining us.
Thank you for having me. So I first want to say I didn't realize how bad my bio sounds, because when I hear people that are only in policy, my first question is, well, what do you really know about the topic? It's a lot different, as Ginger said, admiring the problem than actually trying to solve the problem and work it. So I've only really been in policy for the past 5 years. 25 years prior to that, I was a practitioner, a systems engineer, working in computer network operations, cybersecurity. So I've, been on the other end where policies are working, and I've, seen firsthand that usually the people who are closest to the problem understand what needs to be done in terms of solutions, policy, regulation, but the policymakers don't necessarily understand that. I also tell people, believe it or not, Congress is not super cyber savvy. So, one of my main job at FDD, Foundations for Defense of Democracies, is helping doing that interpretation of, what is the real vulnerability, what is the threat, what is the issue, and then what does this solution mean? What is this technology? It sounds kind of simple, but it's as you can imagine, can really get into the weeds and become very difficult at times. So one of the things I want to bring up in today's discussion is a paper I was able to work on last year. Ginger mentioned it. It's the Cyber Physical Systems Resilience paper that was a product of the Presidential Council of Advisors in Science and Technology. It came about under the leadership under Phil Venables and Eric Horvitz, who were the PCAST leads for technology. I'm sorry if you can hear my dogs. They identified a real problem with critical infrastructure and resilience, and I've seen that too. So they asked me to join the working group, and we put forth 4 high-level recommendations to the White House on how to ensure resilience. And I'll just say that the first issue, not necessarily a recommendation that came out of the paper, but it is that culture of, just saying resilience. I myself come from a computer science, cybersecurity background. And so I think I was fortunate to come into the field as it was being developed. When I entered the field, it wasn't called cybersecurity, it was called computer network operations. There was no such word as cybersecurity. And my first day on the job, with that first week, they only gave me a general idea of what I would be doing. You're supposed to be protecting the networks, protect the networks. And so when you ask questions like how and what do we do? They're like, we don't know, figure it out. We have some tools have been procured. Tell us if we need to buy other tools, figure out the processes, develop it. So this is in the late 90s when we didn't have certifications, there weren't frameworks, we didn't have the publications in NIST to point to, which I think was great because it allowed people to think and discover what the best solution was to move forward. But then, you know, frameworks are great, regulations great. And now, however, we have so many frameworks, so many point of references that I feel that cybersecurity has really become more of a compliance checklist in a lot of areas, which then creates this gap in resilience. So there is a difference between cybersecurity and resilience. The ultimate mission is to ensure that you can continue doing business as usual in a degraded state under a cyber attack. If you're in critical infrastructure, you can still deliver water, you can still deliver energy, you can still provide healthcare, you can still do these things. But you know, cybersecurity itself and that very structured system that we set up now has a lot of the practitioners going through and go through the CSF, the cybersecurity framework, go through the NIST cybersecurity catalog of controls, 800-53, check it and make sure you're compliant. And if you're compliant there, you're good. So if you're good, move forward, and that's pretty much it. Or on the other side of thing, you have various compliance regulatory issues. Are you PCI compliant? Are you FERPA compliant? Are you HIPAA compliant? Are you GDPR compliant? All of these different regulatory issues out there cause a lot of fragmented confusion, uneven distributed amount of resources in different industries, different sectors. So it becomes very, very confusing. I often teach on the side, so I'm an adjunct professor, and I'll teach cybersecurity to students, and I'll get the question, what is it like? What do you do? And my answer is always, well, it depends. It depends. Are you working in water? Are you working in energy? Are you working in the defense industrial base? Are you working in a finance organization? All of these different places have different policies, different laws, different direction. And then on top of that, when you look at critical infrastructure, 85% of it is privately owned. So it's going to be vastly different, vastly approached differently in terms of resources and priority, depending on where you are. So if you're in the defense industrial base, if you're in the federal space, they probably have a chunk of money for, here, you have a cyber command. Everyone here just does cyber. Everyone here is dedicated to protecting of the systems and ensuring that they're able to work. But if you're working in a commercial industry, you have to make that argument to the CEO, the CFO, the COO on why are we going to pay more money for more resources for something that may or may not happen. And if you are a computer science, a cybersecurity person, you can't speak to them and say, well, we believe there could be some type of technical issue, which would cause some technical issue, because all they're going to hear is blah, 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 blah. You have to be able to explain that in terms of protecting their streams of revenue. So what is the organization doing? How are they making their money? And then what is the risk to how they are making their money and what their mission is? So it's very important to go through and ensure that you understand that language and you understand the space that you're in. So in terms of policy, there's that as I mentioned, the fragmented authority and governance across all of critical infrastructure. And when I say critical infrastructure, I know there's a varied audience here. We have 16 designated sectors of critical infrastructure. Each sector has then a designated sector risk management agency that provides them with the guidance of what they need to be doing for cybersecurity. And it's really interesting. If you're familiar with the Colonial Pipeline incident from years ago, most of the East Coast didn't have access to fuel, gasoline, because there was an attack on the Colonial Pipeline, and they had to stop the flow of fuel up the East Coast. I had done a cross-sector analysis prior to this, and I was looking at each of the different sectors, each of the different authorities, all of the rules that they follow, and just lining them up according to the cybersecurity framework. And some sectors give very clear guidance. You have to do this, you have to do this, you have to do this. Everything within NIST, all these different areas, follow every task within the CSF. Other sector risk management agencies were more like, do some protection, do some detection, do some recovery, but again, not super descriptive on exactly what they had to do within the sector. And they didn't give a lot of guidance on, okay, how do I do that? Where do I get the resources to do this? Who's supposed to be doing this or showing me how to do this? Where's the example of this? And that one particular sector really stood out to me. And I always tell people, it's usually surprising, especially to students, like, do you know who is in charge of the security flow of fuel in the pipelines? It's TSA. The same people at the airport. They're responsible for the transportation of things like fuel. So when you looked at the guidance that they had for their sector, it was pretty minimal. Like, just do some cybersecurity, which I've seen a lot over the past 30 years. Usually cybersecurity is a very vague requirement that people point to in requirements and contracts, and then make it cyber secure. I don't know what that means. I've done systems engineering myself. As I said, I'm been in the field forever. When you tell me to make something cyber secure, I still have no idea what that means. You have to approach it from an engineering standpoint. What is the requirement? What is the metric? What is the threshold? What is the objective? What exactly is the intent of what you're building? And then what are those parameters around it? So, I've been promoting, and I'm all for, kind of stepping outside of that, clearly defined cybersecurity framework that we've set up for the community, and getting more into look at the resilience of again, the mission and the system, the organization. It gets beyond just the technical components, look into the people's processes, technology, and then how do all those things work together to then meet the objective of the organization. Identify what the minimal viable objective or service is of that organization. When you, again, look at typical and traditional computer science, cybersecurity kind of guidance, you have a database or a system, and then you have a backup process. So if something happens, it's all or nothing. Now, a system went down, and you've got to go through and recover all of this data or the backup capability, and it's not going to be immediate. So that means until that whole process is then brought back up online, you can't do anything. Your organization can't do anything. They're pretty much dead in the water. So as it applies to critical infrastructure, that's unacceptable. You can't have a water treatment plant or a water organization that isn't providing water. You can't have energy company that's not providing energy, healthcare that's not providing healthcare. These are the critical services that everyone relies on every day of their life. So within the report that we had put out last year, the PCAS CPS resilience report, one of the recommendations we included there was for every sector of critical infrastructure to identify what their minimal viable objective or service is. And it sounds like common sense, but they don't have that. They provide water or they don't. There's some issue. But if you go through and you identify a requirement, like in engineering, what exactly is the requirement for water distribution or water availability. So you could have, bounded impact requirements. So no more than X amount of customers should lose access to water for more than Y amount of days or hours, some time period. So if you identify, okay, regardless of whatever happens, the minimal we have to do is provide so much water to so many people within so much time. And then once you have that kind of metric identified for the entire organization, you can start to go through and trace that minimal viable objective to your critical functions that support that particular capability and requirement. And then you can go through and then trace the technologies that then support to those critical functions. So now you have the critical technologies. And then you have the ability to go through and start prioritizing, your recovery processes or ensuring that you have redundancy where you need it. And it's not an all or nothing. So now when you have some type of cyber attack, natural disaster, whatever it is, something that's going to cause a degraded state in your organization, it's not oh, we were hit with a cyber attack, we can no longer operate. It's oh, we've been hit with a cyber attack and we will be able to operate through it. We have set up our systems so that we have the continued operations with our priority data, our priority processes for our priority customer to meet our minimal viable objective. And so, as I mentioned, it seems like common sense, but across all sectors of critical infrastructure, this simple requirement was not in place. So this is one of the I think the big requirements that came out of the paper. One of the other requirements that came out of the paper that I was very excited about, that it got into the paper, and I'm still working on this to get some traction, is to implement the cyber-informed engineering, principles, concept into engineering programs within the different universities and schools. So I've approached the ABET certification group, ABET being the group that certifies a school and says, okay, you're a certified school to teach engineering, mechanical engineering, aeronautical engineering. So when you graduate, you're a certified engineer. You went through an ABET accredited school. Engineers don't have a requirement to take cybersecurity courses. So they're building things like airplanes, bridges, buildings with elevators. All of these things are now interconnected with cyber components. Everything you touch pretty much is interconnected with cyber components. Yet the engineering curriculum and discipline itself has not been updated for over 25 years. So when you look at the technology that goes into everything, and I bring up elevators because this always freaks me out. When you go into a newer building and they have those elevators that you don't hit the up and down, you just type in the floor number, and then it says go to elevator shaft 3, and then you get in and there's no buttons on the inside of the elevator. It just takes you to elevator 3. So it efficiently then distributes the people to the floors that they're looking for. I don't know why, but I just feel like I have no control once I'm in the elevator and I can't just get off. It's taking me where I wanted it. But usually in building specifications, even just in buildings, there's requirements that you have to have certain specifications for everything, but on the technology side, nope, not a lot of regulation there. So that's an area that there's a huge gap for, and not just building, but again, aeronautical engineering, mechanical engineering, all of these different engineering programs. So the recommendation to go through and insert some of these principles of CIE into engineering would allow for engineers to look at the possibilities of an intrusion to a system before they build something out, building airplane, bridge, whatever it is. And they would understand that there's an attack surface area that exists, and you can minimize that attack surface area by re-engineering it. So if you can design something securely, that's fantastic. Now you're going through, you've thought through the consequences of, if we leave this area here, this could be a foothold for a compromise. This could be an opening in our attack surface that would allow someone to come in, get control, do these things. And I tell people on the cybersecurity side, especially in academia, they're going to harp on you that it's about protecting the data. It's the confidentiality, integrity, and availability. You'll hear the triad 100,000 times throughout your career, the CIA. But it has gone beyond that. It's really about the safety of people and, ensuring our way of lives. Everything has a cyber component. And when you get beyond the IT side of things, which I find there's a little biased in the cybersecurity education there as well. Everyone knows about IT, not everyone knows about OT, and they don't understand the operational technologies and the requirements under them, the physical and kinetic piece of this, which then leads directly to safety. So it's not just CIA of data, it's safety of people. So you might talk to some people and they'll say, oh, we'll just go to the backups. Something happens, who cares? You can't do that in OT because it's safety. You have those robotic machine arms, you have SCADA systems, you have dams, you have other type of machinery where you have people around. You have the ability to then cause catastrophic effects if there's an issue with the cyber components that have been compromised or not working. So the OT side, I think, is a big gap. I recently went to a conference over in Dubai, and it was really interesting to me that they had this whole layout for the UAE on what their critical infrastructure looks like, and then the critical components within there, and the cyber ramifications that could happen. And then in the background, they had this very large dashboard of how many sectors are affected by different OT issues, 30% in water, 20% in energy. And I looked at this and I'm like, well, this is amazing, because this is exactly what we had recommended also in the PCAST paper. We had recommended the stand-up of an organization, the National Critical Infrastructure Observatory, where we as a country would have an organization that has visibility into all sectors of critical infrastructure, and we would see what their security posture is, the resilience posture. But again, that's very difficult to actually achieve, because 85% of critical infrastructure is privately owned. So it's really like herding cats to get things done, and you have to be able to convince people, carrot or stick kind of recommendations. Do this and you get a tax benefit, or don't do this and there's some type of penalty. So those type of conditions usually put on. But when you get to like the idea of a national critical infrastructure observatory, it would act like a digital twin for, again, all sectors, so that you can see what's going on. Then you have organizations that are reluctant to share information. I'm not going to share information with the government because we have these laws. I'm under GDPR. I can't share European PII or anything dealing with it. I could be held in some type of failure for compliance if the wrong thing happens, or if you get compromised and that reflects poorly on me. So the technology itself, there's capabilities out there to help share information, but not widely distributed evenly amongst all these different organizations. So all organizations then have their own strategies of how they implement these different ways forward. So after that particular recommendation, I kind of started digging into, okay, how could we go through and help encourage organizations to share information so that we understand what's going on. It's important not just to say like where we have these CVEs or this is where we're vulnerable, but to also understand what are the interdependencies of these organizations. So if we have something like a Log4j incident, who's got Log4j in their systems? Everyone's got Log4j. Do they know they have Log4j? No. So, could you go through, find some obscure piece of software that's, deeply buried inside some software package, someplace that everybody has, corrupt it, and then crash all sectors of critical infrastructure? Yeah, you could. So, if you don't know that, again, all 16 sectors of critical infrastructure all contain this one particular critical component, software piece that they're not even aware of, you could cause, again, mass catastrophic incidents. But if you understand what's there, then you can, have protections, identify it, understand where there needs to be more varied software or not the same software components. So anyway, the Critical Infrastructure Observatory, identifying those critical components is important, identifying those interdependencies is important, but then also removing some of those obstacles to communicating with the government, with each other, the sector, what are they, the sector councils out there, you're sharing information with them, the sector risk management agencies, sharing information with them, and being able to remove the fear of information being compromised or lost or out of your control. So there's technologies like zero knowledge proofs or tokenization that you can bring into the fold and incorporate into your strategy for minimizing or eliminating data exposure, so you're able to share information in a secure way. And I don't want to say, share information in a secure way, because I would say 90% of the people out there are then going to say, okay, we'll encrypt it. Well, that's not good enough. As technology continues to advance, encryption itself is no longer going to be reliable. We're looking at the, over the horizon, just past the evolution of AI, quantum computing, and the rise of the crypto-relevant quantum computer machines that'll be able to break encryption. So there's, processes underway now to go through and migrate from everyday encryption that people are using, like RSA, to post-quantum cryptography, like Crystal Kyber, Dilithium, Sphinx, so that we're prepared for those threats of tomorrow. So let me see where we are on time. I think we're almost about 30 minutes into this. I've talked a little bit about policy, a little bit about regulation, a little bit about technology. I'm going to scroll through my notes here and make sure I have everything. And I think that is about it. I covered, most of the points I wanted to cover. So I'll stop now and open it up for any questions. And
Sure. Folks who have questions, please put your Q&A on the chat, or the panelists or anybody can feel free to ask questions right now.
And George, do you mind if I take advantage of the pause to ask one?
no, please, just don't make it hard. I don't look stupid in front of everyone.
Okay, this one's one I know that you have a lot of enthusiasm about. As someone who doesn't have a great deal of understanding of how technological policy moves into implementable legal structures, I really enjoyed the work of the Cyberspace Solarium Commission, because they took technology as an input. They really thought with both technologists, with business leaders, with legislators about what was needed, and they crafted materials that lawmakers could use and pass and evaluate very effectively. Can you talk about the process of moving from sort of, again, this technology input, we need things to be better, all the way to, hey, lawmaker, here's some sample policy in case you want to take action?
Yeah, absolutely. It's technology is taking off so quickly. I've always said policy is super slow and it's always a lagging behind. And we've gotten to a point in cybersecurity where, it's very compliance driven. I'll do what you tell me to do. And no one's telling them what to do until there's a policy. So then you have things like, now everyone's using AI. What's the policy on that? Well, I don't know. They're still working it out. It's super slow. We're figuring it out. But, to answer your question, I'll first discuss what is the Cyberspace Solarium Commission. So the Cyberspace Solarium Commission was, stood up under John McCain a couple years ago, 5 years ago, a while ago, because he saw that cyber is a nonpartisan issue that's affecting everyone, and in Congress. Again, I think I said this, believe it or not, Congress is not super cyber savvy. So someone needs to feed Congress some smart cyber recommendations on what needs to be done to ensure that we have protection of critical infrastructure and a way forward in cyber legislation. So under John McCain, he stood up the Cyberspace Solarium Commission, congressionally mandated body, stood up under the leadership of Mark Montgomery, who works with me at FDD, Foundations for Defense of Democracies. And within that commission, there were a couple of lawyers. There were like a handful of congressmen and a handful of former cyber executives from different major departments. So, former cyber lead at Homeland Security, former cyber lead from DNI, congressmen like Congressman Langevin, Congressman Gallagher, Congressman Sass, Congressman King. So again, it's not only Republican and Democrat, but we had an independent in there. And they got together and asked the big questions, like what do we need to do? Where are we going? Who's the belly button for cyber in our country? And they went through, made a list of recommendations, and with some of those questions and recommendations, they put forth their solution. And I think that the beautiful strategy of what they did is they wrote it in legalese. So you didn't just hand over like, here's some great ideas, but here's an actionable, it's already written up in your language, the way you can just insert it right into law kind of capability. So they did that. And with the example I gave, like who's our belly button, they had a recommendation in there for we should have a national cyber director and an office of the national cyber director to lead all of the one ring to lead all rings, because you have Cyber Command, you have NSA, you've got Homeland Security. Who's really in charge? So they did this, and then Congress then had one of the commissioners, Chris Inglis, be the first national cyber director. So they put together this list of again, recommendations. I think they have implemented 80% of the recommendations. Every year, the FDD will have an event, and they go through and give you the status of where we currently are with the implementation of the recommendations. Things have changed, and time has gone by. I think we're at 85% right now. The Cyberspace Solarium Commission officially did sunset, after here's our report. But it was so successful as a nonpartisan group of people that just want to make good things happen and protect our country, that it's continued. And now it's known as the CSC 2.0, and it's housed under FDD. Also, besides Cyberspace Solarium Commission, those relationships with Congress that Mark has, as we go through and we identify these issues in critical infrastructure or cyber, wherever it is, we can bring to him and to his people and to our FDD action arm. These are recommendations we have for law. So, coming from a background of doing a lot of defense industrial support, working for DoD, I did a lot of, you do it because of section whatever in the NDAA. I'm like, all right, we do it because of the law. So I just point to, here's the requirement, here's the compliance mindset. I'm just doing it because it's law. Now, I get to work in that field where I'm like, well, this should be a law. This should be a requirement. So, an example I have is, working in the supply chain of software, and then making a recommendation. If you're working with the Department of Defense or in the federal space, you should be required to provide them with a software bill of materials so they know exactly what they're getting within their software. So I give that to Mark, he hands it to his people, and then they circulate it amongst the different folks in Congress that would be interested in that topic, and then it gets into the NDAA. So that's where the compliance comes from. And I see a couple of hands.
Andrew Ginter, why don't you ask the question?
Hi, Andrew. Good to see your name here.
Hi, good to see you too. Sorry, I just turned my mic on. Thank you for the presentation. My question has to do with resilience. I mean, resilience has been the headline in the OT security space for 5 years. We are starting to see concrete guidance for resilience come out in the form of the CIE initiative. I'm a huge fan of the CIE initiative. We're starting, I was surprised to discover a couple of months ago, everyone's heard about NIS2 in Europe. There's also the CER, a resilience directive to the member states saying pass laws on resilience as well as cybersecurity. I just saw stuff come out of the Danish legislature that is one standard for Danish power and oil and gas industry that integrates resilience, engineering resilience requirements with cybersecurity requirements. to me, this is the right way forward, integrating these. Are there other examples? Is this happening in your space, in other parts of the world?
So yes and no. Also to your point, when I was in Dubai, I was talking to the head of Saudi Aramco, and I asked him, what do you do for OT cybersecurity? Like, what do you follow? And I kind of half expected him to say ISO or some Saudi Arabia Institute of Standards. I don't know. Like, what do they follow? And he said NIST, which really surprised me. I didn't expect him to say NIST. So NIST. I tell my students, I tell people it's the national standard, but then internationally you want to follow the ISO standard, but no, internationally they're following NIST. And so with NIST itself in August of this year, I don't know if you saw this or not, but they put out a new version of the catalog of controls. So NIST 800-53 5.2.0. And in there, they introduced a new control, SA-24, which is designed for cybersecurity. So it's that, or engineering, designed for cyber engineering or engineering of cyber. So it's engineering aspects. It's like the CIE control. So I thought that was just phenomenal that it got into the catalog of controls. Baby steps, very baby steps, because it did not make it into the baseline, the 800-53 B that then says these are the controls that you have to follow for whatever system. Also, the NIST resilience piece, if you look at the CSF, the Cybersecurity Framework 2.0 that came out in, I think it was March of last year, or late February of I think it was March of last year, 2024. They updated the framework, and they have in there one of the categories is resilience, which I thought was fantastic. So you have resilience now being addressed in that framework. However, when you read the details of it, it says, organizations and systems will meet the requirements for resilience. I'm like, yeah, there aren't any. They don't have the requirements. So again, baby steps, they have it in there, but organizations don't have those requirements on, well, what does that mean exactly, the requirements for resilience? So, to answer your question, I see it permeating. I've seen draft legislation come across my desk. Hey, George, can you look at this? Or can you read this policy brief? Or can you read whatever? And usually it'll start off with cybersecurity or the protection of, or ensure cybersecurity. And I always cross that off and I say, no, the resilience. We're going to ensure the resilience of something. Because again, cybersecurity is just going to be put up your walls and your moats, and let's hope they don't get in. That doesn't help anyone, because they're gonna get in. They're being delivered to us through our supply chain. They're in. So how do you get through that? So you have to ensure the resilience aspect. So I hope that answered your question.
Thank you. And we
Indeed,
have
thank you.
Dr. Anurag. You want to ask the question?
Sure, yeah. So thanks again, George, for very nice insight. Just to follow up on the last question, that when we think about security and resilience, things are getting more sophisticated and quicker by attacker with AI, right? And at the same time, we need to respond with proactive and corrective action and policies and all those things. So what we should be doing different, given that attacker becomes more sophisticated and more quicker to implement and launch an attack compared to what it was like few years in the past.
Yeah. So what should we be doing?
Mm-hmm.
It really gets back to, I guess, the methodical approach of what is your minimal viable objective in service? Like what is your organization supposed to be doing? And how are you ensuring that's going to happen in a degraded state while you're under attack? And I mean, the technology, like I said, it's taking off. AI is taking off. Quantum's right on the heels of AI. I remind people all the time, if you've seen the movie Terminator, it starts off in the year 2029. And I tell people, once quantum gets here with AI, we're in the year of the Terminator, and we're right on track. So in 4 more years, we're in the year of the Terminator. So it's important to not approach systems and systems protection in that, and this is going to sound terrible, especially at a school, in the textbook way that they're teaching you, like go through and do these things, add these controls in this methodical way. understand your organization, your system, what's the priority, have a strategy, implement those technologies to ensure that redundant strategy and the ability to work through some type of degraded state. And when I say strategy, you know, I'm a computer scientist myself. My undergrad is in computer science, my master's computer science, my doctor's in computer science. And no one's ever really sat down in a class with me and said, let's talk about strategy, you know, a layered strategy approach to get through degraded times of operations. Let's incorporate things like zero knowledge proofs. Let's incorporate things like tokenization. Let's incorporate you know, aspects of security at every layer to ensure that, you know, regardless of when and where the adversary is coming in, you can continue to do business. So I would say it's, again, very important, you know, like an engineering, you know, approach to understand how all these things work together and how you're, you know, protecting them and ensuring that continuity of business. Because policy is not going to individually, you know, tell you how to do it. They might give the high level, these are the guidelines, but if you really want to protect your organization, your systems, you're going to have to dig into what's the best strategy for your organization.
Barry, you want to go next?
Yeah, sure. Here, let me get my camera on. Georgiana, this is a really, really awesome, cool topic. Had a question about when you talked about what is, you know, the OT, IT, things like that. One of the things that I've run across over the last few years is the discussion about, you know, the NIST controls for OT, things like that. And I think that what you're referring to is that there's really no concept as to where that line ends and begins, or begins and ends. And so what I found is it almost confuses the nature of our business by saying IoT, OT, IT. It really is what's on the wire at the end of the line and how important that is, to your point. I was wondering if you could talk about that a little bit, about how we standardize language, because that's going to be what drives our language forward, our regulations, our concepts, and the way we interpret and address things. I'm just curious if you had some thoughts on that.
Yeah, I do. And I don't know if these are great thoughts or not. I associate OT with OJT. You know, I've seen in a lot of academic institutions, it's all IT. Maybe there might be, all right, today we're going to mention OT. This is what it is. All right, back to the IT. And then you get out in the world and I think as a practitioner, there's not a lot of cross-pollinating of maybe sectors. So if you're working defense, you're working defense. If you're working water, you're working water. If you're working OT, you're working OT. So there's already like a big gap and void for the OT preparation. So it seems to be a lot of the OJT, you know, on the job training aspects for OT. The other thing on the common language, it's you know, I'm working on a project right now on quantum. Super confusing because there's different words: quantum safe, quantum secure, quantum resilient, PQC. What do these words mean? I don't know. There's no standard definition for them. And even PQC, post-quantum cryptography, NIST defines it as their selected algorithms, whereas other countries, it's just an algorithm that could go through and then be protected against a CRQC. In technology and OT, what I would love to see, what I would love to start working on is you know, playbooks, like playbooks for the OT organization and critical infrastructure. It's so varied. You know, what are your legacy systems? What is your particular mission? What are your restrictions? That I think people generally just kind of like, it's too much of a unicorn. Everywhere you go, it's going to be different. It's not going to be standardized. IT, it's the same thing. You got a firewall. You have the same systems. You can in the market area produce a tool, and it's going to apply to everyone. OT, nope, it's going to apply to this organization here that's doing this one particular thing. And then you've got to incorporate it into their operations and what they can do with their legacy systems. But I think if we were to go through and start to delve into what that looks like and develop these playbooks, that would be very helpful for organizations and provide a source of education for the OJT aspect of the OT. I don't think that answered your question, but those are my thoughts on it.
Thank you.
Thank you, George, for your wonderful, fascinating presentation. Appreciate for all the thoughtful questions. I think we're going to move on to the next presentation. Thank you, George, for your time this morning with us. It's a great honor to have you.
All right, thank you for having me.
Thank you.
Now, moving on, the next session is a panel session. We have, I'm going to let Dr. Anurag and Barry moderate the session, and both Ginger and I will listen and will ask if we need any questions if you want to. But I think let me introduce the panel members and then the moderator next. Can you show the next slide? And okay, we have Barry Jones is one of the moderators for this panel. He began as a network and telecom engineer working natural gas and electric transmission, SCADA, and data center projects across Southern California. More recent, he has managed teams of information systems security officers, where the team focuses on cybersecurity engineering and projects and solutions and assessing and developing and aligning FISMA, NERC, CIP, and governance, risk, and compliance programs. There's too much text here. His recent work was in the Department of Energy, where he managed a team of cybersecurity information assurance professionals supporting NIST and NERC, CIP, ONP policy. His work includes multiple NERC, FERC, and NIST audits, mitigation management, continuous process improvement, industry collaboration, and the federal government supply chain. He has also collaborated with multiple trade associations, WICF, IEEE, NATF, USEA, EEI, EFCOG, and recently completed work on simulated multinational electric grid cybersecurity incident response exercise. That's quite a mouthful, a lot of experience. Barry comes in. Thank you, Barry, for agreeing to moderate. The next moderator for this panel is, we have 8 panel members, so we need 2 great moderators who's going to support, have an interactive panel. Dr. Anurag Srivastava from West Virginia University. He's the chairperson of the Computer Science and Electrical Engineering Department and the Raymond J. Lane Professor at West Virginia University. Dr. Srivastava leads a team of faculty, staff, and students passionate about advancing computer science, cybersecurity, electrical engineering, computer engineering, AI, and you name it. He served as a technical lead and lead co-I of the $30 million UISS Center, driving advancements in renewable energy integration and decarbonization. His research interests include data-driven algorithms for power systems operations control, with high-impact project resulting in tools installed at utility control centers supported for more than $60 million by funding agencies such as USDOE, NSF, and so forth. Dr. Anurag is well known in the community for smart grid, I don't want to say a few words. Thank you, Dr. Anurag, for being here. And Ginger, why don't you introduce the panel members? Can you show the panel members, Tanzim? Maybe next slide, Tanzim. Yeah, maybe a few words.
Thank you. For our panel today, I'd like to introduce some mostly folks that we heard from yesterday, but we have 2 new speakers as well. So Jamie Sample from Deloitte is here, and he performed our keynote yesterday. Jason Nelson and Mike Prickett talked yesterday about advancing energy challenges and how they're overcoming them. We have Joseph Asef Turner from Maya Security, Charlie Cunningham from the city of Sacramento, and joining us today, we have Andrew Ginter from Waterfall Security, who will talk later this afternoon, and Chad Uland from Minnesota Power. Welcome, panelists. We have several questions for you.
Okay, I'll let Barry and Anurag lead the session.
Okay. Hey, thank you. Welcome, panel, and thank you for joining. So I'm going to start off with a question that I know is probably near and dear to your heart regarding AI and its use in the utility sector. And what I'm curious about, or what you could discuss, is what are you seeing from your peers from industry regarding the implementation of AI in, say, SCADA environments for water, things like that, for automated switching? We've gone from manual processes in some cases to SOARs and things like that. So looking ahead, what do you see in there? Can you talk about that?
Well, I can personally say I have seen a client uh, begin the process of implementing an AI switching tool. And I had a conversation with Nelson Muller. I don't know if most people here know Nelson, but he's a EE PhD and one of the founders of OATI. And we had lunch the other day, and we were talking about AI and switching. And he looked at me and he said, people could die. And I said, "You're right, doctor." And so it's unbelievable to me. And we talked about, what's gonna have to happen. And I said, this is America. We like to run with scissors, and we wait until we fall down with scissors sometimes before we learn. And we had a discussion about, do we have to have a blackout, or does somebody have to get hurt for these things for somebody to pump the brakes? Because right now I'm not seeing anybody pump them.
I'll add, we work with a lot of different organizations. And I mean, on the defensive side, people have said they're using AI for 20 years. Okay, on the intrusion detection side, before there was machine learning, there was expert systems. So intrusion detection, alert correlation, AI is in a sense everywhere already and just going to be used more intensely going forward. But we're also seeing AI used fairly intensely, fairly increasingly. Not large language models, not looking at English, looking, or whatever the language of the day is, looking at history, looking at desired outcomes, looking at actual outcomes, and just optimizing process and sending commands back into the process saying, operate this way when I see this happening, to operate more efficiently. The goal is usually more efficient operations. That's what AIs are being used for, and they're being used in lots of different industries, and it's just going to increase.
I would add, though, Barry, we are also routinely receiving contract amendments from customers mandating that we employ no AI in the solutions we provide them. And we are routinely receiving these contract amendments.
I think this is a great discussion. And Mike, I think you led me to a second question that I didn't really want to throw out there. But this is really a supply chain issue. I think what you're talking about now, you've kind of moved into supply chain. How do you negotiate? How do you kind of navigate those contractual obligations? And then you've got legal, acceptable use of materials, all of this stuff, right? So is there somebody that can talk about that? I mean, and then how do you balance the cost of business? You have a great business there. You are very good in what you do. And how do you balance that cost and that, future state with keeping in business? It's got kind of something the supply chain is bringing to you, whether you want it or not.
Yeah, so, like in the case where somebody sends me just a blanket mandate to employ no AI in the services and products that I provide them, that's too broad, right? And so we look at it and we say, my gosh, AI does an amazing job of system documentation, right? And system documentation is always grossly lacking, especially in systems of the complexity we have. So to say that we can't employ AI for system documentation is overreaching. That's a benign use of AI in the context of what we're doing. We're not letting it into the operational decision-making sphere here, right? So we're having to sit down and look at these things and try to generate our, uh, I guess, ask, if you will. These are the things we want to be acceptable uses of AI in our world. Some of the other things that are really exciting to us are the natural language query, right? There's always a desire to unlock people's data to them without the cumbersome traditional approaches of building APIs and building reports and all this stuff. So we think that, natural language querying is a really, really valuable use of AI that is safe in terms of, what we're doing for people. So we're trying to sort of itemize what it is that we think we ought to be able to do and to go back and make our case.
Hey, Jamie, you have some perspective here.
Yes, kind of going along with what Mike was saying there is I think you really have to think about where and how you're applying the AI, right? Because it's a tool. But I mean, we're seeing utilities looking at things like rate case development, leveraging AI. They're doing storm response. We're doing vegetation management components because how fast it can analyze things that humans can't, right? So I think, if you look across the value chain and the spectrum of all the different, activity areas from supply chain all the way out to field operations you have to understand it and say, where does it really apply, right? And how do we want to apply it? The whole thing around the agentic agents is a force multiplier, right? It still requires human intervention, but it allows the human get to the answer a lot quicker, right, than 100% autonomous. So I think, if you look across every aspect, even from finance and customer analysis, bill notifications and stuff like that. There's thousands of use cases there across that's applicable. It's just you have to have it's like, people are going to cloud and without a strategy, it's running with scissors. You've got to have your AI strategy, right? What use cases, how do you want to apply it? We're seeing everybody now saying, the only way to go is private LLMs, right? Because public LLMs are dangerous. So we're seeing everybody, going to saying, okay, I want to build my own private LLM so I can manage any hallucination, other things like that, right? So I think it's like anything else. As disruptive technology comes, you have to have a strategy and understand where you want to apply it. And if you don't have that, somebody mentioned running with scissors, you're just running with scissors, right? So it's getting your AI strategy together.
Thank you. It's a good topic. Andrew, you're next, and then I've got a couple others. You're muted, Andrew. Yep.
Sorry.
Need some
Just
AI automation.
Just to add a couple of data points, what we see is that the industries that are adopting AI, in my experience, the fastest are also the industries that are adopting cloud connections the fastest. And sometimes the AI is in the cloud. And to me, what the AI, in my experience, there are exceptions, tend to be used for is improving efficiency, making difficult decisions about optimizing the process. Because most of us, yes, safety is our first priority, reliability is our second priority, but efficiency is also a priority. It does no good to have the world's safest, most reliable train system if the population can't afford to use it. Efficiency is important. So AI contributes to that. The design pattern that we see used to assure, the engineering grade design pattern that's used to assure safety is ancient. It's the use of independent safeties. If the AI is sending commands into the physical process and it either malfunctions or is sabotaged, or the connection to the cloud is sabotaged, have an independent safety. Deciding, answering the question, is this process physically safe right now, tends to be a much simpler decision than how do I do this optimally? Have an independent safety backstop. What's new is that we need cyber independence as well as historically electrical independence and other kinds of independence that we've mandated for our safety systems. There are exceptions. The exception that I know comparatively little about, but I worry about, is self-driving cars, where some of the safety systems are themselves AIs. And if anyone knows much more about that than I do, please let me know why that makes sense and how that's working.
Charlie. Thank you, Andrew.
Thank you. But to me, I think for our organization, it's like any new technology comes along, there has to be a defined acceptable use, right? And then we do the benefit analysis. Is there a value to employing this technology? And as Andrew touched on, I mean, there's a lot of different things we could kind of call it AI that we've been using for a long time. But in the water industry, right, there's licensed, operators that are required for the certain decisions to be made. And I think just along the lines of the autonomous cars, right? Well, now we have this whole other cloud of driver's license situation going on in the country. But where you've in the past where we've required somebody to have demonstrated that they're qualified to make those decisions, I think that that's going to be where we're going to draw the line for a while. And I do agree that as much of it as people, everything that we have currently, other than some of the protection and intrusion detection that we use, is all on-prem. And so when people start getting forced to go to the cloud for different subscription services that they can no longer get just because it's not available, or somebody's made an acquisition and they want to use this business model, so what you've done before you can no longer afford at a 600% increase. I won't name, but some virtualization acquisitions that we've been faced with, right? Those are going to be not cost effective. But as people go into the cloud, I think they're not going to really know, right, how much AI is being used there unless they're paying attention and there's some acceptable use, policy as to where they approve the use of AI.
Yeah, I think that touches on back to the supply chain again. Great questions. I'll turn it over to Anurag. Thank you.
Thank you. Yeah, I think great discussion on AI applications. As I was listening to that, I was thinking that those AI applications which are already in practice, what has been experienced so far in terms of accuracy, and how do you address if you have a false positive or alert fatigue, or depending on the applications?
I'll start off if you like. The field that have the most experience with is on the defensive side. People have been using expert systems before there was AI. Now they're using AI. They're doing alert analysis. They're doing brain blank, anomaly detection, looking at what's normal and saying, has anything changed? And the common wisdom in the space for 20 years has been, you can tune these detection algorithms to be more or less sensitive. The more sensitive you tune them, the more alarms you get, the more false alarms you get. The less sensitive you tune them, the more alarms you miss. And so there's a sweet spot. Basically, you look at how many alarms can we afford to investigate in a day? And you can't produce more alarms than that, or you can't investigate them. And so it becomes a question of the capacity of our SOC, the capacity of our incident response teams, the capacity of our security analysts, dealing with the accuracy and the intensity of the AI. So in that domain, it's kind of well understood how you have to tune things. I'm not familiar with other domains.
Yeah, so I can speak to that in our world. I spoke yesterday about a real-time communication protocol called e-tagging, and it's used for physical power flows on the grid. The average e-tag's life cycle is about 25 real-time messages. We will flow thousands and thousands and thousands of tags a day, each of which have 25 component messages to its lifespan. In the context of intrusion detection, if you sort of take most of them out of the box and turn them on in our environment, it is the most overwhelming thing you've ever seen. The sheer volume of messages, the alerts that get kicked out, no one could possibly keep up with, not even remotely keep up with. So then you start detuning it, dumbing it down. Well, it quickly gets to a point where everybody's sitting around saying, there's still an absolutely overwhelming volume, and what value are we creating? Because literally we would have to just have a team of people sitting there at the desk investigating these things. And then, you know, when you talk about intrusion prevention, well, we're talking about real-time power flows on the grid. If that tool makes any sort of mistake and prevents a power flow from happening, that's clearly a really big problem. So in our context, because we are resiliency and reliability first, those tools present just enormous challenges for us. And of course, we get asked about them constantly, but I think what we've agreed on with the DOE and the federal agencies is that our job is resiliency first, and that those tools represent real risk to resiliency in our situation.
Great, thank you. So let's do Joseph. I've got one for you, Anurag, if that's okay. What are you seeing internationally? You know, we heard Georgina speaking about you know all the different bodies and the different frameworks and things like that. And what is it that you're seeing internationally to maybe align things, or challenges or gaps that you're seeing that where, hey, one country may be seeing something, another, or do you see, looking into the US from an outside perspective, some things that maybe we're not seeing?
In terms of what? Of policy, of AI?
Policy, cybersecurity, technology.
Great. So I think yeah, we're all crediting Georgina, but yes, I think first off, we really, when we talk about ICS and we talk about industrial systems, especially when we talk about energy, it's resilience and it's safety and it's production before we even get to talk about cybersecurity. And at the moment, there was this, we were talking about running with scissors. So globally, looking globally, it's a lot of people running around with a lot of scissors. So we're talking about, yes, if we're talking about regulation, so everyone has their own, you know, set of rules. And we've been talking about this with DOE for a while now. And if you look at all regulations, you look at NERCSIP, you look at NIS2, you look at 62443, all of these would probably have 80% of their controls in common. And still, everyone's looking for their own personal brand and regulation. So at some point, I think we're going to see, and this is a personal opinion, one is some kind of convergence or trying to build some kind of benchmark to have a common language for everyone to talk with. And the other thing, I think that AI, especially now, I'm not sure if this trend is going to last, but especially now, it's both a positive and negative effect on resilience. We've been seeing when we've tried getting AI into threat intelligence, when we were trying to get it into decision making, it's always kind of a double-edged sword when you could see it being detrimental to resilience, and you can see it improving it. So it's a lot to take, and right now I don't think we have any clear answers on the role of AI, except for that we know it's probably here to stay. So we need to find ways to manage it better.
Thank you.
Yeah.
Virginia, I saw that you were nodding your head with a lot of this. Do you have any thoughts on that? I mean, I know you're looking at the cyber-informed engineering part. You're trying to get ahead of the curve, right?
Well,
Maybe have some thoughts on that.
I do. What we noticed, and I very much resonated with the idea that 80% of these controls are similar. They're framed a little differently. The hows might be a little different, but they are ultimately digital controls that we put in a digital environment to protect against a digital or information security outcome. Where cyber-informed engineering is different is that we looked back to the ancient or at least mature safety practices that industry had and said, hey, I care about what happens in the digital plane, but the thing that will really hurt my consumers, hurt my business, the thing that's existential to me is what happens in the physical plane if I run critical infrastructure. IP is less of an issue for me. It's important, but it's not my bread, it's not my blood. And so we took those engineering practices and tried to say, hey, how could I use a pressure relief valve, a time delay relay, a spillway, some other controls to prevent the impact of a cyber attack, assuming that all the digital stuff makes it hard for the adversary, but the adversary has increasing intelligence and increasing capabilities on their side. Physics is the thing that will stop the adversary because I can't get around the physics. I can get around any of the digital things that can move physics, but once I get to the physics, I can't push digital technology against physics. So I am hoping that, even though I know it, I don't want to create another brand of thing, but I'm hoping that we can get these ideas into the NIST controls and in some of the other critical resilience-based approaches so that you can take credit for the things that you do for safety as cyber controls, thereby aligning your safety and your cyber programs. And then you can explore additional designed-in safety-based controls that then limit your susceptibility to cyber attack. So thanks for the opportunity to talk about that.
There is a question, Barry, on the chat. It says, how important is it to correlate OT behavior with IT signals, such as VPN, EDR, cloud logs? Can you share a case where this cross-correlation made the difference? This is a question specifically for Andrew, or yeah?
I can give you a shot at it, but I am not an incident response expert, so I defer to the others on the call. But let me give you just the beginning of it. Intrusion detection is an imperfect art. We catch some, we don't catch others. Intrusion detection takes time. Sometimes we catch them in time. Sometimes we don't. But it is essential. Okay, we should not be operating our infrastructure without some kind of detect, respond, recover capability. This is part of the defensive posture. What I will say is that I was talking to on the podcast, this is public knowledge. I was talking to the head of Enbridge's incident response, cyber incident response team. This is as far as I know, the world's largest liquids pipeline in North America here. And I said, you do OT incident response. How do you stay in practice? I mean, I've never heard of a public incident where the bad stuff got into OT and shut a pipeline down. Okay, at Colonial, the bad stuff was in IT, and we shut down in an abundance of caution. How do you stay in practice? He says, Andrew, we practice constantly. Everything that goes wrong, there's 3 different teams that converge on it, trying to figure out what it is. We're trying to figure out, is it a cyber attack? Someone else is trying to figure out, is it a network fault? Someone else is trying to figure out, is it a physical fault? Is it an automation fault? And whoever figures it out first tells the others. We share information and, solve the problem. We got to keep the pipeline running. And so I would imagine that a team like that would find it useful if there were some correlation capabilities between what they're observing in the physical process, what they're observing in the automation process, and what's happening on the IT network. That's a clue that maybe the cyber team should be looking at things more intensely or looking at a particular piece of the puzzle more intensely, while the other teams are trying to figure out, was this just the failure of a valve that needs to be replaced now? So I think it's useful to have these data sources, but beyond that, I don't study that piece of the space. Sorry for your confidence in me. I defer to the others here.
Jamie.
Yeah, adding on what Andrew said, I think in the discussion earlier between, taxonomy and what we call things, right? Drives me crazy, the IT, OT, IoT discussion and all of that. These are all just assets with capabilities, and we just need the capabilities and skill sets in those areas, right? I mean, if you think about it, is Microsoft IT? We got Microsoft control systems, right? Running on Microsoft. So all of a sudden, is that IT or OT? So all these are just digital assets and physical assets, right? And we need the skill sets in my mind, the skill sets and capabilities to manage those. And going back to what Andrew said, is that unified, I mentioned it yesterday, my keynote is having that unified response where you bring across that unified team that has the views from their point of view and their expertise to quickly correlate and respond is critical, right? I've been in so many incidents, like I said, where it starts out in operations on a physical device, and if we knew about that, it would have been an early warning that something went upstream or downstream, and vice versa. Right. So I don't think we can disconnect or keep looking at all this stuff in silos. I think we have to, and we can't keep trying to categorize it as IT or OT, because we spend more time talking about what's IT and OT than we do solving the problem. Right. And so mine is it's digital assets. All the information matters. We need to look for anomalies across the ecosystem, regardless where it's at, and try to stop it as early as possible, right? Because there's a lot of warnings and early indicators. I mean, if you think about network operations, right, or application monitoring, they start seeing disk usage go up. Well, maybe that's a runaway process, or it's somebody doing something they're not supposed to do, right? So, and if you don't bring the team together to have that thought of, wait, what's causing this, and that curiosity, then it becomes a reactive event. So I think, going back to Andrew's, is you've got to pull everybody together, watch the systems, watch the anomalies, be curious about the environment. Don't try to get into what is this IT, OT, or whatever. Have the right people with the right skill sets for the right assets, and have them in the room for the discussion.
Joseph has
Joseph.
Right. So I apologize, James, but maybe I'll slightly go on a different vector here.
That's okay.
I think Virginia made a great point. When we're talking about IT/OT, I think it's not necessarily who talks IP and who does and who doesn't. It's more of which components are connected to the physical process and which are not. So
Yes.
if we're looking at an IR for IT, you'll be dealing with, you know, the Active Directory, you'll be dealing with protocols, you'll be dealing with anomalies on communication like disk usage and CPU and memory and that fun stuff, registry, whatever. Sometimes you can do a lot of damage, and we've seen this over 15 years ago with Stuxnet. You can do a lot of damage with very little anomaly or even no anomaly at all, because the commands that the PLC sent were legitimate, right? There were
Yep.
no actual anomalies, but if you would have monitored the actual physical process, you would have seen that. In going back to my talk yesterday, we're not monitoring the physical process at all. And this is
Correct.
something that we need to start doing. It's one of the projects My Security is doing right now. This is, if we're not doing this, then you're absolutely right. IT/OT, same thing. If we're discarding the physical process, you're absolutely right. I think we're in the wrong for discarding the physical process.
Yeah. And I think we're in violent agreement on that. I agree 100%, and I like the way you framed it. So
to follow up on that question, you know, when we talk about IT, OT, and physical system, and this convergence team, which will look at all these data and analyze, I mean, this team has to come from, you know, most probably existing team, which is IT, OT, and you know, physical system monitoring team and decision-making team. So what, you know, what organizational and cultural barriers you see? And do you also think that technically we need a tool to correlate those things, right? Because right now,
yeah, a great question. And that's one of the things that, you know, it's really interesting when you start talking, and that's why I'm like, you know, pushing to say, you know, you have to get away from the IT/OT discussion, because within organizations, it all of a sudden becomes an organization discussion, right? As soon as you say OT, oh, that's operations. As soon as you say IT, that's CIO. Oh, we don't like each other and we don't talk. Well, let's quit labeling things, because every time we label things, everybody automatically goes back to organizational hierarchy. And so that's my point around, we've got to break that. We've got to break that mentality and that mindset that the terminology is connected to organizational hierarchy and authority, right? Because all of a sudden, that's where you get into this big issue, right? Take your organization hats off and all of that, get in the room with your expertise and go in and do it at that, versus, you know, hey, this is an us them some game, right? So that's why I think that's, you know, I think organizational hierarchy, where the money flows, things like that, still creates silos within the organization, right? Around that. So I think there's significant cultural and organizational boundaries that's got to continue to be broken and discussed around that. So and then I think the technologies, as Joseph was saying, you know, if you look at behind that demarcation point to the physical side, is we're relying on those digital sensors to give us that insight. But if those digital sensors are wrong, we don't know what's on the backside, right? So we've got to, I think we got to go back to, you know, basic engineering functions and do separation, you know, separation of safety system from control system. We've seen a lot of convergence around that just for simplicity and communications, things like that. Nuclear still does really well at that. I was just watching a video on nuclear refueling yesterday, and how much eyes on and how much they do around that backside to validate that everything is still mechanically there and operating like it should. So I think there's a lot of technologies out there, from cameras, visualization, and all of that can get you that, and smart placement of sensors. Diversity in sensors around that, so that you can have, am I getting, misreadings from different sensors, have diversity. I do think the discipline of separation of safety and control, command and control, has to come back into play. We don't do it very well, especially as we've seen digitization of safety systems and all of that. You can get it's on the same collision domain as command and control. So I think we've got to separate that to drive integrity. So some of my thoughts around that.
Yeah, Andrew.
I will agree and disagree. I agree that silos have to be broken down. We need to solve this problem. When a factory drops, does the OT team say, how did this happen? Oh, it was because we depended on an IT service, and the IT service was crippled by ransomware. Therefore, we're good, no problem. The factory's dropped, but that's not useful. When the factory drops, okay, the CEO, if they know what they're doing, are going to take a couple of heads, the head of operations and the head of IT, and start knocking heads together until the factory runs again. Okay, he doesn't care. She doesn't care whose fault it was. We need to cooperate to fix the problem. But I will disagree somewhat. There are material differences between IT and OT, and they are, many of these are in a sense superficial. Let's talk about the fundamental differences, the differences that will never go away. Consequence is one difference. Okay, we cannot restore human lives from backups. Safety is important. It will always be important. And it is something that IT tends to be blind to until they're educated on it. So consequences, one, usually, not always. Okay, some simple manufacturing systems really can be modeled as IT systems, but critical infrastructures tend to be have a different animal. A second one is, let's call it more theoretical. The asset on IT networks that we seek to protect is information. Protect the CIA, AIC, blah, 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 the information. The asset that we usually seek to protect on the OT side is physical operations. We seek to prevent sabotage of physical operations. We seek to prevent, usually, espionage, primarily, of the IT side. Back of the envelope, okay, we're not talking absolutes here. We're talking usually it's different. And the cybersecurity theory, okay, Bell LaPadula versus Biba, the theory of sabotage and espionage are different. In practice, to me, the single biggest difference I see is on the IT network. Information is the asset. Quick, encrypt it all. That's how you protect information, for one of the tools for protecting information. On OT networks, information is the threat. The only way you can cyber sabotage an OT network is if attack information gets into the network. That's the only way to change from a normal state to a sabotaged state. And so all incoming information flows are not assets. They are potential threats. So it's a lot of the same technology, but the emphasis is subtly different. And in a sense, it's too subtle. Okay, too often we have teams doing this because they're using the same words to mean different things because of these differences that aren't well understood. So to me, education is critical. Yes, break down the silos, get the teams to work together. I'm on record recently saying, when we have this spectrum of assets from IT on one side and safety on the other, and everything else in between, where do you draw the lines? Well, that's an organizational problem. It matters less who is doing the work than it matters that the work is being done correctly. Wherever the equipment is in the spectrum of consequence or in the spectrum of espionage versus sabotage, it needs to be managed correctly according to its position in those various spectrums. let's start figuring out how to manage them correctly. And then, the organizations can argue about who's in charge.
I see Virginia hands up. Thank you, Andrew.
Thank you. I want to come at this from a different place. I think it's easy to get caught up by saying that these different organizational teams don't want to work together or don't have the right language. But also, I learned from Daniel Kahneman in Thinking Fast and Slow that every human is desperately trying to preserve the glucose in their brain. And so when they enter a threat-laden situation, they just want to know, what do I have to pay attention to and where can I turn my brain off? And so a lot of what we see as that organizational infighting is really that preservation campaign in the brain of someone saying, okay, I'm going to retreat to the thing that I know well, burn less, my brain is burning less glucose. And I just want to know what in this challenge space I can ignore so that I can stick into my lane. So I think it's important to acknowledge that human behavior, help ensure that people understand the corporate risk envelope. At my organization, there are two things that we do very poorly. We don't connect our researchers to what means success in our outside world. What does it look like for the company to do well? A lot of our researchers, they know how to publish a paper, but they don't really know what makes the better organization look good. Equally, they don't know what an existential threat to the organization looks like. So if I'm in the IT department, I think an existential threat is maybe an exfiltration of information, some kind of phishing campaign. And the chief financial officer would say, look, that's not a great day for us, but I don't care about that. That's not my worst day. So I think also teaching people about what is corporate risk, how do they then apply their knowledge to corporate risk, and encouraging them, hey, we all want to ignore the parts of the problem that are alien to us, because it's going to take a lot of energy and glucose for me to learn about finance or about logistics when that's not my field. But if we are solving a collective problem, you have the help, you have other organizations, you can get subject matter expertise, but you really do have to push yourself and solve those challenges.
Thank you. Interesting thoughts. Yeah, Joseph.
Right. So I'll try and kind of combine, because there were very smart talks just now. Looking at, if we separate the two people, so we'll have cybersecurity people and we'll have the engineers, and engineers are probably, especially electricity and the guys dealing with electricity and big machinery, very, very smart people. Now, if we look at a cybersecurity incident or cyber incident, for everyone, the initial contact, if you will, would be, let's say, we're using this when we're doing tabletop exercises. So one of the valves doesn't go to auto, right? It's stuck on manual, and there's no way to bring it back to auto. And this is, if you look at a cyber incident evolving, that would be the first step. Now, if you asked any kind of cybersecurity person, what would you do? Then yes, bells are ringing, we got to run, we got to do this, we got to do that. And we have usually the CISO and their team coming in, and we'll do this, we'll do threat hunting, we'll shut down that thing. And the engineers will go, what the hell are you talking about? We get this, twice a day. It's a malfunction. And for engineers, usually a lot of the stuff is, it's a malfunction. It's a regular, it's a daily malfunction we're dealing with, to a fault. A lot of the times I've seen an H-class 800 meg go down, and 45 minutes later, they had a press release saying it's a malfunction, right? There's no cyber involved. So on one hand, you definitely need to get your cybersecurity people educated on, like Virginia, what you said about what are the success factors for that factory. But on the other hand, you need to get those smart engineers to realize and take in the dangers of cyber attacks. And I'm guessing that the truth is somewhere in the middle between the two extremes.
Very interesting. Yeah, I think, my original question was cultural and organizational barrier, and maybe technical barrier too. I think there is a fourth element too, which is a cognitive barrier. And, just like electrons in the power grid will follow and find the least resistance path, humans will also do that. And when that happens, I think there are two different kind of behavior, right? So I think Virginia was saying that they will find that, least resistance path at that time, which they are more comfortable with, maybe during emergency process. But during normal process, we have to show the organizational and goals for that. And then, do you have more thoughts on that? Or I think that fourth and maybe a little bit technical too, we did not talk about that.
Great responses all. So I'll dial it back less technology here, and I want to show my friend Prakash. So I always wear this shirt. So if you know Hindi, this is
Yes.
Alexa, right? And so in essence, for you who don't know that, it's a friend of mine gave that to me about 10 years ago. And he told me about it being target, keeping a goal in front of you. So we're being hosted here with our esteemed colleague Prakash at UND, and he's the busiest person I know. He's online 24/7. I start wondering if he's really AI or not. So anyway, the question I have for all of our panelists is you've touched on education, paying attention, glucose, Virginia. That's pretty awesome. I love that analogy. Labeling equipment and assets and engineering skills. So we're here with the University of North Dakota, and we're looking at a future generation of folks coming up, and they're being impacted by AI right now. Do they use it in the classrooms? The professors and the teachers across the US are saying, kids are using AI to answer questions and things like that, to do their homework. So there's a lot going on in technology in humanity. And so my question, just a couple bullet points for all of you, because we're all at various different areas of our career and have impacted in industry differently. What would be a couple recommendations that you would provide to the students who are going to be the next leaders, the decision makers, and experts in our field? And just a couple things that maybe that they would want to know, thinking ahead when they go back to their target. That seems to be a moving target, right? So why don't we start off and just go around the room, and Prakash, you can feel free to join in that one also. So go ahead.
I want to learn and listen from you guys. I'll keep I'm going to listen.
I'll go first. One piece of concrete advice I give to people is spend some time studying attacks. If we want to design effective defenses, we have to know what's coming at us. A concrete example, I had a colleague of mine 10 years ago, joined up. We did a lot of on-the-job training. At some point, they wanted the certificate, CISSP, which was the thing to get in the day. To a degree, it's still the thing to get today in the space. So he went to CISSP training, week-long intensive training. Came back. I said, "So how'd that go?" It went great. "What did you learn?" "I learned everything." Blah blah blah. I said, "Great. So pop quiz. Here's the network architecture for a typical power plant, gas-fired power plant. How would you protect it given the knowledge you've gathered? I would put one of everything in. The antivirus server goes here and an Active Directory there, and the firewalls. And I said, great. Here's the attack scenario. Bang, bang, bang. They're through. We're down. Oh, he said, one of each isn't enough. No, one of each isn't enough. We have to understand attacks. And the second reason to understand attacks, beyond designing our defenses, is comparing the strength of two different defensive postures. How would you compare the strength of two different designs? I don't know. Is one more compliant with a standard than the other? No. What we do is look at a representative cross-section of attack scenarios and ask which attacks does the one design defeat with a high degree of confidence that the other one does not. This is how we compare. So I would encourage people, among the other things you learn, do learn about attacks. We don't all need to become penetration testers. Okay, we don't have to be able to carry out the attacks ourselves, but we have to understand enough about the attacks to be able to apply them to a defensive posture and answer the question, will this get through?
I'll take a shot next. I think you have to immerse yourself in the environment that you want to be knowledgeable of, right? I've spent 20 of my 25 plus years of career, I've spent 20 of it as a practitioner at utilities. And once you're in the field working, you've got all different elements that goes into decision making than you do in a lab or somewhere else, right? So everything from economics, OpEx versus CapEx, rate cases, how much you get from the state versus the federal. All of the economics of running a business goes into security, right? I was just talking to some of my peer chief security officers and CISOs, and I'm like, people think that as a CSO that I'm sitting there thinking about security every day. I'm thinking about how to run a business and meet budget and targets, right? And so I'd say immerse yourself in the environment you're wanting to be an expert in, and look and see what are the elements that come into play and how to do them the most efficient and effective as possible. The other thing we're talking about AI, and Barry, you asked about AI and the leverage of AI. I did something recently on LinkedIn that I talked about AI makes me think harder. And what I've learned about leveraging AI is syntax, as probably everybody knows, and especially anybody that's a lot younger than me probably has already figured it out. But syntax really matters. And what I find happens is using AI slows me down to think about how do I ask the question or pose it. But when I get the answer, I still challenge it. I argue with my AI agent all the time. I mean, my wife will be like, who are you arguing with? I'll be like, my AI agent, because they don't know what they're talking about, right? So I think it's really important to, like I said, immerse yourself, slow down and think about the context of what you're asking, leveraging AI, and then don't believe what you get out of it. I grew up in my dad telling me, believe nothing you hear and only half of what you see. Right. And I think we have to keep that skepticism. We have to keep the challenging going. And so don't accept what it gives you.
Yeah, I'll just say,
Go ahead. Go ahead, Mike.
Sorry, from somebody in the trenches, I'll just say, I was listening to a doctor the other day who had gone to one of the top medical schools roughly 30 years ago, and he was saying how his recollection is that they had a 2-day session on nutrition, and that was it. They didn't talk about nutrition back then. What I find is that when we bring on new, and again, we run a singular team service model whereby there is no separation of IT and OT. We treat it as a team that is to deliver a service to the software side of our house. So it's very integrated. But as we bring on new members of the team are very scary to all of us because inherently they come in, and especially now we're in a world where everybody just thinks everything should happen nearly instantaneously. And what we don't find is people coming in and saying, tell me what's really important here. Well, in our case, that's resiliency, right? So we literally have to put people on limited access to everything for 6 months while we kind of beat it into their head every day, measure 3 times, cut once, because we're about running the grid and our resiliency is what will be measured by. And we literally have to fight this fight to just constantly try to get people to think about the culture we're trying to run the right way, and that is resiliency, resiliency, resiliency. So when you design things, design them with resiliency and redundancy in mind. As you go to say, well, I'm going to improve this in some way. Well, it's sort of the Hippocratic Oath, right? Do no harm. And it's very, very hard for us to instill this in people because everybody comes in and everybody's a cowboy and they want to just say, I could do that in 5 minutes if you just take the shackles off. And I have to say, the shackles are never coming off. We're running the grid. And so I would love it if engineering education included sort of this get people to understand what is my mission here? What is most important here? So that everything I do, whether that's design or implementation, that is on the forefront of my mind. Because we fight that fight in building out our teams with people just so wired to, I could do this, I could do this, and in this week, we could change the world. Yeah, changing the world's fun, but not when you break it along the way. So I would like to see engineering students learn more about the fact that there are different profiles of company, right? Some companies, their data is most important. Well, in a grid ops setting, all data is historical by the time it becomes data. The vast majority of it is historical and represents very little risk to anyone. The operational capabilities, the best ability is availability, right? And uptime and keeping that grid running securely and safely is the mission. But we don't have engineers coming in asking those kind of questions. Instead, we have to beat it in.
I'll jump in. James, it sounds like we were raised in the same household here, and with my Navy background, I get the situational awareness aspect as well. From a different perspective for me, I actually have a college freshman and a college junior in the College of Science and Engineering here in Minneapolis, and I think about them when I talk to the new hires is use AI as an assistant. It can't make the decisions for you. You're the human. Use it for research. Use it for questions. Be curious. But have skepticism, challenge it. 30 years down the road, I know what good looks like. I know what the output I'm looking for is. I still challenge it, like James said, but I use it as a tool, as an assistant. I'm not looking for it to do my job for me. It's just making part of my job easier by collating information and data and formatting it and challenging it. So that's what I tell our new hires is, AI, especially public AI, don't ever put anything in there, company, customer, or absolutely not personal, because you've just lost control of it, but use it as an assistant to help you with your job. And over time, you'll understand what good looks like, what a good output looks like, and can see the hallucination and the misanswers. And as James was saying, with prompt engineering, massage the data back and forth to get the right answer, but it takes time to get there. So be curious, but be skeptical as well. And that's the approach to all of our new hires when we onboard them.
I have a question. What happens, when you look at some natural disaster like earthquake or tornado or flood, how do we prepare these tabletop exercises to make sure that, those bad actors make use of these natural disaster compounded risk, when we see, how is the cyber is going to play a role when this unforeseen, uncertain circumstance happens, and then they're trying to exploit our critical infrastructures. And how do we prepare ourselves for these type of circumstances? What are your thoughts?
I can speak to that a little bit, and I think there may be other practitioners here who have insight on this as well. One of my favorite things that we do in the United States is NERC's GridX exercise every 2 years. And I have some challenges with it, but I'm just going to speak to what its purpose is. NERC runs an exercise called GridX that every power entity in the US can participate in. There are a number of scenarios that are passed around. And by the way, it's happening now. I'm getting alerts in my email that are GridX exercise alerts. I'm not reading them, but it's fun to always know that they're there. Power utilities can decide what parts of their organization they want to kind of involve in these exercises, how deeply they want it to go. But these exercises allow them to explore these challenging scenarios, like we have a natural disaster, and we have, while we're trying to do recovery, we have a cyber actor who tries to get in on the reduced resilience that might be there in that moment. That's the good news. I would say what we can do is encourage our asset owners to be very brave and to dig deeply into these GridX scenarios, to put more of their capabilities at risk, really ask the challenging questions. Because if we treat it, and I'm a child of my generation, so I'm going to say, if we treat it like a Dungeons and Dragons adventure, where I can say, oh, I'm going to take my +1 sword and I'm going to go out and kill, the adversary. That's easy to say in a tabletop, and it's easy to roll up some dice and make that work, but it's much harder to do institutionally. So the good news is, in the US, we have a every 2-year exercise that really allows our asset owners to explore scenarios like that. The bad news is we're not leaning into that as much as we could.
Yeah, I would say this, as it pertains to SIP, for example. Well, we find, our customers are allowed to make their own designation as to which assets are SIP relevant. And we are very, very surprised at a lot of the situations where they elect not to deem something, a platform, a specific function, as being SIP applicable, because I think any rational view of it would say, no, that is in fact what these controls exist for. But because they can self-elect, we see everybody just going around it.
I'm going to add on to some of this too is, and I'll echo what Virginia was talking about on if you look at the purpose of GridX and other exercises that we have across the industry, really purposeful. They're good at the industry level. I think at the utility levels, when they participate on, like you said, Virginia, they need to challenge themselves. But how do you do things more incremental, right? And bite size, right? I think, I've worked with a lot of, clients, as well as in seed. I owned emergency management at my last company. We would run about 80 all hazard drills a year. But we would be very targeted in the impact and all of that, and what areas we'd look on. And so the idea was to take incremental baby steps around it, right? Don't try to boil the ocean around it. Let's identify. It's kind of going back to, what are you trying to defend against? It goes back to your scenarios, right? And I always thought, when I go to the board, I can't tell the board, hey, I can defend against anything all the time, every day, no matter what, right? It's here's the scenarios we designed the system to be able to operate and defend against. And that's what we test and validate on. If there's something net new, that's a process of change management, of saying, okay, there's a new threat or a new element that I need to take in consideration, relook at my system. Can it manage or counter that? Or do I need to make changes, add that to my use case, and then rerun that again, right? So you're always running against what did you design the system for, right? And I'm like, you run the models against it and do all hazards. Like you said, is when's the best time to attack somebody's when they're looking somewhere else, right? Or when they've got assets and resources deployed managing another crisis. And I think it goes back to being intentional about, can your organization handle a complex event well or not, and exercise against that. I think we do really good at storm responses. We do really good at single events. We do good at things that we have known the last event. We do really good at preventing going forward or responding to. It's that all hazards and complex event that we have to be purposeful and carve out the time, funding, resources to be able to do that.
In our case, we take, again, our uptime as the mission. So for us, historically, everybody had production and DR, and the question always was, if I had to turn on DR today, what in it is actually going to effectively implement the mission? Well, that's always a scary thought, right? Because there's so much room for these things to be out of sync. And if they're out of sync, then if we have to rely on the other asset because of a natural disaster, for example, will it serve? And so we have tried to eliminate that element by doing what I said yesterday, and that is we run from multiple live active endpoints. So, for example, I don't have to sit and question whether or not the latest release of the customer application is in fact applied to all sites, because if it's not, we're going to know it immediately. So we have that instantaneous feedback that we have really, really high redundancy that is active and proven at all times. And then the few elements that are not, so like the database, it can only be live in one facility at a time. We will run drills to actually run the processes to fail the databases from one building to another, and that all the applications automatically repoint using a technique that we use. But so we try to make sure that as many redundancies are actually employed and live at any point in time, which proves that they're up to date and able to serve if any one site is lost. Eliminating as many questions about a given location's ability to serve. And so that's how we try to distribute the resiliency, if you will, in a proven way.
Andrew?
The concrete example, in my understanding, what you're asking about here is a hurricane comes through, and in most of our region, most of the power is out. And so we have mutual assistance arrangements, personnel and equipment from neighboring regions come in to help us restore power. And throughout that emergency, those people, I mean, everything is automated today. Those people need permission and access to help us bring the automation back up, to use the automation to bring the physical process back up. We accept the risk of, the increased risk of compromise in that scenario because, bluntly, we're already down. What can the bad guys do to us? We're already down. So to me, there's sort of, and again, I look at this from the outside. I talk to people, but repeating what I've heard, there seem to be two things to keep in mind about scenarios like that. And the reason we have to practice these, because it's not easy, is one, if part of the system is up, our control center is still up. We have a redundant control center. It's up, it's intact. We still have to protect the control center. Okay, we need, if we can, be judicious about how much permission we give out to the visiting people, because part of the grid is up. The part of the grid that's up, we should probably be protecting a little more aggressively than the piece that's down. And the second is, when all is said and done, there is a threat that we often don't think much about. It's the risk not of an attack where you steal something, but an attack where you leave something behind. We close up the substation because we're finally done repairing it. Was a Raspberry Pi left behind? Was a laptop left behind taped underneath a server device? Generally, the people who come in to help us out are trustworthy, but there's a lot of people flying around. Did an intruder get in by putting on the yellow life vest jacket saying, "Hello, I'm a worker, I'm allowed in here." Um, we need to look for different kinds of symptoms of compromise after one of these events when we're in the cleanup phase than we would in normal operation. So that's my 2 bits worth.
Charlie?
Well, thank you. Yeah, to me, it comes back to this is where your CIE really shines, right? That you have backup contingencies in place, and that folks know how, the operational plan for those when other systems are down. And a lot of what Andrew said, I mean, as far as if you're already down, we're already running in hand or we're already doing a manual operation in those cases. But the bigger part is that we're paying attention after that type of an event for now how are things behaving differently than they did before. But so yeah, pretty much he covered what I was gonna say. So.
Okay. Any other questions? I know we probably want to plan for this 2 hours, but it may not last 2 hours. We just maybe close in any last minute thoughts as we wrap up the panel.
So one question is from Craig in the chat.
Oh yeah, go ahead, Anurag. I didn't see that. Yeah.
Yeah, it's the first one is, how can utilities and infrastructure companies better facilitate a partnership between the cyber and physical operation sites of the house, providing a greater familiarity and comfort between them to be more effective as a team for emergency response? Yeah, Charlie, go ahead.
Just from personal experience, I became a manager over the SCADA team on our water utility over 15 years ago, and when at the point in time when I came into that role, there was a lot of finger pointing going on between the people that handled the hardware and the endpoint devices in the field, or the people that were handling the HMIs and the PLCs, and so just as Andrew mentioned before, the factory's down and oh, not us, right? That was happening all the time. And so I restructured the group to where, there was ownership from the endpoint device to the control room, and having all those skill sets within the groups. And I think, I completely agree with a lot of what James said is we get so caught up in the labeling. It's really about defining areas of responsibility, because there's so often that we're running the exact same hardware, some cases even the same applications as our enterprise side of the house, right? It's just areas of responsibility and who has ownership, and making sure that the skill sets within that group, that area of responsibility, can actually handle what they're responsible for. We do share contracts, we do share information, we share training with our enterprise IT counterparts, but it's really about defining those roles and responsibilities, and who's responsible for which assets for our group.
And Charlie, you're absolutely right. And I'll add on to that too. I think having a rotation process is really well. It works really well at accelerating that. Barry knows this, when we work together at other organizations, like I was hiring or I was bringing over engineers directly out of the operations team to help on the cyber side and assigning them back because they knew the system inside and out, right? And we could teach them the cyber side, and then they would rotate back out. So I think, you have to look at career development and rotations around this will really help accelerate that and drive that acceleration.
I'll just say that one thing that's been enormously helpful to us is building our security and infrastructure teams around people with military backgrounds. It's been enormously beneficial. They sort of have a natural understanding of this has to be owned and there has to be an answer, and how to make a team amongst themselves with accountabilities that's sort of natural to them. And so anytime we see an engineer with a good military background, we're very interested, because it's just a natural thing. And I literally have made it very clear that our preference is to hire people with military backgrounds.
Very good. I think follow-up question is like, how can university help in this kind of like mindset for and encouraging students to get trained on interdisciplinary teaming and thinking about other aspects? Yeah, go ahead, Joseph.
Right. So when you're talking about these two very, very different types of career paths, one would be electrical or mechanical engineering. The other one would be cybersecurity. So to have someone do both well is an impossibility. You really don't have that. You could have engineering aware cybersecurity people, or you could have cybersecurity trained engineers. I have to say I've yet to see anyone who does both well. In the mindset, actually, a lot of the times will be completely different. So if you, and I think I found it funny when Barry asked Prakash about what suggestion you have, what advice you have, and he said, "I'll just sit here and listen." I thought that was the best advice. Just listen, learn, and if you're doing cybersecurity, you need to be very, very aware of what the engineers are doing, what the process is. Be very aware of the physical properties and effects of what the machines are doing. And then if you do training for those engineers and do combined training and drills, I think you get to that point where you have some kind of beneficial coexistence, I think, and both teams will work at common goals.
Very good. I saw Virginia hands up, but maybe she has same thoughts.
So I just wanted to say that we have some materials in cyber-informed engineering that would allow engineering instructors to introduce some of these cyber-based issues in even a basic engineering lab. So instead of a device mechanically failing, let's explore the cyber failure and then examine what engineering we would bring to the table. I have seen I know Georgia Tech has a drones class, and I call that engineering informed cyber, where they have a lot of cyber students looking at the idea of a drone. It has to stay up in the air. It has to fly and hit a target. And so they're trying to do cyber things to it, but they have to take in the engineering and physical aspects of this device. So those may be two sources.
You're cutting out, Ginger. But anyway, I think we will take the last 5 minutes or so to close this panel in 11:15. I know that you're basically spending, thank you for all your time, but I think we'll ask Andrew to ask his question, and then we'll wrap the panel in another 5 minutes.
Well, I wasn't going to ask a question. Sorry, I was going to observe that one of the things that helps enormously is teaching people not just to cooperate in teams, but teaching people the limits of their knowledge. I remember this was close to 20 years ago. I was at Industrial Defender. We would go in to do risk assessments. People commented that they half the time they bought our products because they liked our people. They would contract out a risk assessment to an IT contractor. The IT contractor would come in, into a server room with 1,000 machines in it and another 1,000 PLCs, and plug their laptop into the first network report they saw, start a scan, and walk away and say, "This will take a couple hours. Where's the coffee machine?" While behind them, one bank of lights after another goes red. Our people would come in, having experience with OT systems. They would put their laptop on the ground, their bag, and they would put their hands behind their back, and they would look around and say, "Explain to me what I'm looking at." And they would not move a muscle until they understood what was safe to do and what wasn't safe to do and what it was safe to do it to. And the sense I have working with a lot of fresh grads, the sense that I hear from other practitioners in the space is that not enough people understand the limits of their knowledge. And the sense I have, now I'm not an engineer, the sense I have is that this is something that is to a degree included in engineering training. You're only allowed to practice in a sphere of influence that you're qualified to practice in. That training does not seem to be, in my experience, reflected on the IT side. So to me, this is a gap. Make sure it happens on the engineering side and add it to the IT curriculum. People need to know that, yes, they've seen the whole space an inch deep, a mile wide in the undergrad curriculum. But there's a mile of depth behind every inch of that space. Why do we put shackles on them for the first 6 months? It's because they have to learn this.
Yeah, there's
Thank you.
nothing more scary to me than the routine intrusion, penetration testing we have to do. And I'm very happy when we can keep the same resource for a number of years, because I have finally gotten them to understand you don't do that. Okay, you don't turn this thing loose and go for the coffee machine. Okay, we're talking about keeping the lights on here. And oftentimes, though, we'll go through a cycle of years where we've got a new resource. They're oftentimes very young. They don't ask any of the hard questions, and we have to sit them down and say, "Listen, this is a very critical thing that you're approaching here. It's different than most things you're approaching, and we have to again try to beat it in there." And it would be nice if there was some just like with the engineers, it's that education about sit down and ask these things about this organization and what's most important to it, and it would go a long ways.
Thank you. Yeah. So,
What do you think, Barry and Anurag? Where are we?
well, there are more questions here, but if you need to wrap up, we can.
Yeah, I think unless the panel has something, I'm good. One thing that I found is that it's always interesting, right? Everyone, there's something for everyone, and there's always change. And if you're that kind of person, you have that. If you like something that is process oriented, but I see the one big thing that related to education and process and everything is human factors, just culture. People are always going to make mistakes, and it's going to occur at every level. And so keeping that in mind too.
Jamie, you have something to say? You raised your
Yeah,
hand.
Jamie's got some.
Yeah, I was going to say, and I think, like on the panel here, we disagreed with each other on certain things. We agreed with each other on certain things. I think having that courageousness, we all come from different points of views around it. And just because we disagree don't mean one's right or wrong or whatever. We just have different aspects. And so I think maintaining that open-mindedness, as Andrew was saying earlier, listen a lot, ask questions, don't be afraid to because none of us know everything, and we know a little bit about a lot, right? And so just because of how deep this is, and I think Andrew and I think everybody kind of hit this, is that if we think about what's happening with cloud, AI, IoT, all of that and how it's transforming it's all erasing that really that illusion of isolation, right? You think about forever as, hey, all the stuff is separate and all this it's consolidating together. I mean, if you look at what markets have done around real-time markets have done around integration into real-time operations, they're interconnected like never before, right? Because they have to. How do you get outage information out to clients, or I mean to customers before when the outage? You have to interconnect to real-time systems. So the whole convergence, the AI, everything is just really blurring the line and getting rid of all the isolation that we have. And I think that's what makes this super complex now, more complex than it's ever been in history. And it's only going to get more complex.
Folks, it has been a great honor to have you on the panel. I think you guys have taught us so many today. I think the session is hopefully useful for a lot of us. I think we're going to close the panel session. Ginger, thank you for good moderator, Anurag and Barry for supporting all the panelists. You guys are awesome in all the requests to make this November being a critical infrastructure month, and supporting to do activity like this would help create awareness to the community to see what else we need to do more and educate the students as well. I appreciate for being here, and we're going to close the panel with this. Thank you, everybody, and we're going to join at noon. We have a nice cyber training by INL talk.
Actually, wait, can I inject? It will be 11:45.
It's 11:45?
Don't halfway through, 11:45.
Okay, Tanzim, do you want to show that slide that we have the reminder schedule for the day? Before I forget, what do we have? Oh, there you go. Okay, so this will be at 11:45, so stay tuned for our talk. Thank you, panel.
Thank you very much.
Thank you.
Yeah. Thank you, Prakash.
See you at 11:45. Good afternoon, everyone. We are returning from our break. I hope you had a chance to catch up on all the things that are probably pinging in your mailbox as our discussions are going on. But we are going to move forward. I have the pleasure of introducing to you Jeff Hahn. He is one of my colleagues at the Idaho National Laboratory, and he oversees our operational technology and ICS security training. Do we have a bio for Jeff?
Tanzim, can you show the bio for Jeff?
I'll tell you what, Jeff, why don't you describe your background? You do a wonderful job with it. And I think if you'd like to share slides, you can just share away.
Okay. Help me out. First of all, can I?
Oh, we have the bio here.
That's all right. I'm just to let everybody know, my name is Jeff Hahn. I am a program manager at Idaho National Laboratory doing cybersecurity training, working on both the DOE and DHS side. A little bit of background. I've worked in the past for government, for private sectors as well. Prior to joining INL this second time, I was GE as a product cybersecurity chief, where I worked with the grid equipment, the hardware, software, grid equipment, and working to make them more secure. I also worked at Honeywell as the PSERT, or the Product Security Incident Response Team Manager. And yeah, that's me. So
thank you, Jeff, for being here for this summit. I appreciate your time. So do you have a slides to talk, or you have?
I do have some slides that I'd love to share.
Go ahead. Yeah.
So let's see, I'm clicking the share button.
Are you getting a naughty message?
I'm getting a message that says host isn't allowing multiple presenters sharing it this webinar.
Tanzim, could you allow Jeff to share the screen? Give us a second. Let's see.
Sure. So while we're doing that, let me just give you a little bit of background. Idaho National Laboratory has done a lot with OT security, industrial control systems. We have what we call cybersecurity researchers, aka government-sponsored hackers, to do things, and we've worked with control system vendors, looking at their systems, identifying vulnerabilities, working with them to fix them, and trying to make things a better place. With all of the cybersecurity things that we have done, we were able to take some of those, lessons learned, things that we've learned from, and put them into cybersecurity courses, just to share the information out, do what we can. So we've done that over the years, and it's been going along. So we have several courses that I wanted to share with you and talk to you about. We've got things that are online. We've got things that are in person. We've got courses that we can take on, and travel with and provide training to at different locations. So that's what I wanted to share with you. Okay, looks like I can do this now. Let me know when you can actually see what I think I'm sharing.
Yes, we can see the blue screen with the industrial control system, cybersecurity training offerings.
Okay. So we are off and running. All right. So just to let you know, also our courses, the ones that I'm sharing with you, are all accredited. So if you are in the need for continuing education credits, for a CISSP or a PE or anything like that, we can provide those training credits. So I thought I'd first tell you a little bit about our virtual learning portal, where we have 13 short courses. We have 2 a little bit longer courses, 15 to 20-hour courses. And this is also where you sign up for some of the other DHS sponsored courses. Signing in with a username and password enables you to get to each of these courses and sign up for others as well. So let me tell you a little bit about some of the courses, the short courses that we have. They came from the same general training, but we broke them down into different smaller chunks. This first one, the operational or OPSEC for control systems, is a great overview of just common sense cybersecurity practices. It's a great one to just run through, so go for that. There's others that go for the OT environment, risk, attacker perspective, and defense sections. If there's something that you really want to look, you don't have to start with number 1 and go all the way through, because you're really interested in number 9, you want to get to that. You don't have to necessarily go through all of them. There's no prerequisites for any of these, so you can just jump in and take these courses. These courses are free. All you have to do is sign in and go take these courses. So hopefully these will become helpful to you. They are there. They're taken hundreds of times each month, all over the world. So it's available. Okay. Our 300 course. This is our ICS cybersecurity training. It is online. It's on demand. You get into the VLP and you can take this course as well. This is one of our longer courses, 15 to 18 hours to get through this course, depending on how much time you spend in the labs. The labs themselves are pretty extensive. They are an environment to set up. We have things for you to do within those, but it is an environment. So you can actually do other things if you want to, try other things. It's a true lab. true environment. So it is a prerequisite to another course I'm going to talk to you about in a little bit. But the things we talk about in this course are, well, everybody likes to see how an attack works, right? So we have an environment where we set up with coming from the internet, going into a corporate environment. Then we go through that corporate environment and we find our way into the DMZ, and then pivot from the DMZ into a control system network to take over some control systems and operate pumps, things like that. Just to show you how to, we talked a little bit about what enabled those things to happen. And then we go through and give you some opportunities to do some of your own discovery. So network discovery and mapping exercises goes along with that. Network defense, detection, analysis. The exploitation process, you actually get in, I have the opportunity to work in a tool called Metasploit, probably familiar with that one. And then exploit some boxes that are available in the lab environment. And then finally, the network attack and exploits, understanding how an attacker can work, things that they can take advantage of. We understand that, just like Andrew was saying, if you understand the attacks and the things that the attackers can do, you're better poised to defend against it. So this is a great online course to do, recommend, and of course the link to it is there at the bottom. Now, our 3R1 course, this has been going since 2008, and it's just been pushed around by word of mouth and a little bit of online social media. But other than that, it's a free course. 4 days here in Idaho Falls. We start out with some breakout sessions where we talk about wireless security, again, network discovery, control logics. We have a ICS architect course that is really good. We do the attacker perspective again. We need to understand how attacks work, and a couple courses in defense. But then we have you think about those things through ICS escape rooms. These escape rooms have been around the country. We've been taking them to different places like DEF CON and Hack the Capitol, Women in Cybersecurity, lots of different places. And they have been a big hit. They've been a lot of fun. We incorporate the learning objectives from the 300 and the 301 course here, and see how you do. We work with you as a true learning environment. If you get stuck, we help out a little bit, but not too much so that you struggle through this. So this is a lot of fun. Our last day, on Thursday, we have a red team and blue team exercise. And this red team, blue team exercise, true lessons learned come from this every time. Let me just show you a couple of pictures. Escape rooms, we get pretty involved in there. We have a lot of fun going through whether we're disarming bombs or we're trying to save a space station from asphyxiation because their life support systems have been cut off. We have fun with our with our scenarios. For the red team, blue team exercise, this is done in an environment where there's 4 different control systems going on that have to work together, including power and 3 different supply chain systems that work together. It's not scripted. It is, we take 9 people out of 42 in a class and put them on the red team and 33 people on the blue team, and they have to maintain the entire IT system, the OT system, and try to improve its efficiency, try to make things work better, because of course, the more product we make, the more money we make, and we're all happier. But you've got to protect everything as well. And you know there's going to be a cyber attack. So you've got to work on the firewalls. You've got to work on the IT infrastructure. You've got to work on the OT infrastructure. You have a SOC, Security Operations Center, to monitor all of the traffic that's going in and out of the system and across the system as well. Looking for the bad traffic out of all the different traffic that's going on. We have lots of traffic generation, so it looks like a real environment. And we have a management team too. Of course, we have to implement the bureaucracy that is required to have a true environment. So we try to make this as realistic as possible. And again, like I said, there is a lot of real world lessons learned each time we run this course. A lot of the same lessons every course that are showed up, but people understand things. People understand the difference between, well, why the firewall people sometimes say no, or management, why it takes so long to get through the process, different things like that. It's a lot of fun. All right, so this one's great. So come and join us in Idaho Falls. We have come up with a new course, and we've just started this course this year. This is our Detect the Attacker course. This course is a 4-day course also here in Idaho Falls, working in the same facility that we have the 301 course in, where we share with you our framework of looking for bad things going on within your environment, working the IT side as well as the OT side, combining that traffic, looking for things. So you're looking for, trying to understand all the OT protocols, environmental modeling, your cyber threat, and how you have to interpret that, looking at logs, all those types of things. I'm trying to understand what could happen through your own environment, because you got to understand your environment. All those types of things coming through this. I was in a previous role prior to this, had the opportunity to talk with some different companies, utilities and others, and looking at their operation, we asked, what could you actually see, with the data that you were bringing in? And so we started getting down into the details and asked them, could you see this? Could you see that? And they started realizing that they were blind to some of the things that we hoped that they could see, because they only brought in the data and the logs that they needed for operations. They didn't bring in things that they needed for cybersecurity. So we're bringing this understanding of what actually we need to see and how we need to pull specific data in so that we can actually see things. It's hard to see what you can't see, right? What's not there. So this is a great course for this. And we hope that you'll find more information about it. You can log into this course. It's the same place this link is right here. So you go to that link and you'll be able to find a way to sign in for that 311 course. All right. One other online on-demand course is our ICS evaluation. This helps you understand how to analyze, evaluate, document, and your ICS environment. Going through and understanding, we've only got so much budget, we've only got so much time, so we can only do so much. What do we need to prioritize? And this helps us do that. This course uses the Cybersecurity Evaluation Tool, or the CSET, and it allows you to use recognized government industry standard recommendations, whether you're doing the SANS Top 25, the CISA cybersecurity performance goals, or what have you. There's a lot of different standards and recommend practices that you can test yourself against and see what you can go forward and do. Great course here. Regional training. We work with the CISA regions. There's 10 of them across the United States, and we go to 5 of them each year. And so we're hitting somewhere in the United States for each of those regions every other year. This year, we're working with the eastern half of the United States. And so we'll try to put as much information as we can on our website so that you can find where these are at. What we do there is a 4-day training that we generally do. We can do other things too, but generally this is what we do. We have a 101, 201, or 202. Essentially, we're taking each day, bringing everybody up to the same speed with our introduction to industrial control system security. And then we start getting into some of the details. And on the 202 course, that's our hands-on course where we brought equipment and you're actually working with PLCs, RTUs, and manipulating them. Cyberstrike courses as well, and I'm going to talk about that one next. So our Cyberstrike, this is we call this our Lights Out course. Cyberstrike is a training program, and there are several courses that are associated with Cyberstrike. This first one here, Lights Out, covers in detail the 2015-2016 attacks that happened in Ukraine. It's getting dated, right? It's almost 10 years old since these things have happened. But yet, when we go back and take a look at the details of what happened, and we start analyzing some of those things, they are still very, very relevant for today. So, we talk about the environment. We talk about the differences between the 2015 and the 2016 attack, the breadth of what actually happened. And each of these attacks resulted in a power outage that didn't last very long, but is some of the after effects and what actually happened during the attacks that we really want to pay attention to, because it's those types of things that could affect us, right? That could be replayed on our systems. These are the labs that are associated with the Cyberstrike. And this picture over here in the center, this is our Cyberstrike kit. This is a kit that we bring around with us. And we have groups of 2 to 5 people work on a kit like this throughout the whole this training. So it's very hands-on. You're actually using real equipment with process control systems, with human machine interfaces, with field equipment. So it's all there. It's a whole control system right there. So you can see some of the labs that we're doing that are very relevant, and that some of these things actually happened in those 2015, 2016 attacks and very relevant for today. Another course we have called Nemesis. Nemesis is our nod to the rest. Here we go. To a threat brief. And so we talk about some of these attacks that have happened, these nation state types of attacks and events that happened, right? So the attackers and the events. The labs that we do associated with that are similar to what you might have expected from some of these actors. So take a look at some of these labs, right? Credential harvesting, malware detection, doing ransomware. These are all still very, very relevant for today. So this is a great course. For more information on this, just send us an email to cyberstrike@inl.gov. I'll get that and I'll reply back to you if you have any questions. Other courses that we have associated with this include Shadow Valve, which is using that same control system, but in an oil and natural gas system process. or a compressor station, looking at that. But we're still utilizing the 2015, 2016 information and incidents that go along with it. Storm cloud, we have a wind and solar kit that we bring around, and we do training on that. So we're looking at the cyber attacks directed at those systems. Forensics analysis helps us to understand what occurred and the extent of the compromise, how it happened, those types of things. This forensics analysis course is provided twice each year with the cyber fire training. So if you'll Google Cyber Fire Foundry or just Cyber Fire, you will find this course that is available. It just recently happened in Boston last month. Next year, there is one scheduled in April, but I forget where it's at right now. But anyway, you can find this online. Ginter talks a lot about cyber-informed engineering. This is very similar to this, but a process or a methodology that INL has developed for consequence-driven cyber-informed engineering. What we're doing is we have a 2-day course that will take you through this process. It's called the Accelerate Training, and you can go, it's a 2-day course that walks you through this process of understanding your high consequence events, looking at how, if you had a high consequence events that was caused through cyber means, what you can do to mitigate that high consequence, make it less of an impact through engineering processes. Great process, great information. It's kind of a train the trainer. So you take this course, you take it back to your environment, and you implement it there. ICS Fundamentals. This course is a 3-day course taught here in Idaho Falls, and it's not a cybersecurity course, but there's many people that are very familiar with IT systems and how they work, but yet they struggle when they're trying to understand what the difference is and what's so special about the OT environment. And so this helps you and takes you through using hands-on exercises to understand what a control system is, how it works. You get the opportunity to play with the HMI, develop one, you get to work on the ladder logic. And then there's field trips to different locations here in the local area where you might see a power plant operating, or wastewater, or maybe food or processing, different things like that. So you can actually see control systems in processing in work. If you have other needs, INL has an environment, a controls environment where it's more of a range, not so much training, but a range where we have modeled up different critical infrastructures. You can see here we've got a picture of a building automation system, or a transmission distribution system, chemical process, or compressor station. We've got other skids that along the same scale here that represent other critical infrastructures as well. We bring teams in and we do help them set up with their blue team, and then Idaho National Laboratory is the red team. They're attacking, and we're working with them to help them see and identify the attacks that come through. So this is more of an engagement opportunity versus a training. But there have been teams that have come through, companies that have come through, military groups that have come through that have truly benefited from this. And with that, do we have any questions?
Thank you, Jeff. I think it's awesome. Thank you for sharing all this great resources. Okay, we leave up to the questions and see whether anybody else have any questions on this. While we wait for these questions, who are your audiences? Is it like mostly like utilities, or do we have opportunities for undergrad or grad students also to participate in this training? What is your...
Great question. So yes, this was designed for the industry professional. However, we have many undergrads, grads, interns taking our training as well. So they're more than welcome to take our training.
Okay. You talked about the CSIS regional training sponsored, have you been to North Dakota region, this region, upper Midwest?
We were last year. I think we were in the Dakotas last year. And so we'll come back next year.
Okay. Cool. Andrew, yes, please.
Not a question, but a comment. I took the training, I believe, in 2012, 2013. You were there. Thank you. And I will add that it was my first exposure. I'd done a lot of defensive stuff. It was my first exposure to the attack side of the equation, and it helped enormously. And I was able to attend despite being a Canadian and not an American citizen. If I recall, I was on a sort of a short list or a wait list rather, and there was a last minute American cancellation, and you couldn't find an American to fill the spot. So you said, Andrew, do you want to come on down? I said, yes. 3 days later, I was there. So enormously beneficial, the 301 course. I have not sampled the others, but you've reminded me they exist, so I'm going to go and see what you've got. And I did want to say thank you.
Well, thank you very much. Appreciate that.
Jeff, do we have a catalog or handout for people that I can send out to the registered participant? Do you have any catalog or something on the courses?
I do. Let me forward that to you, so you can send that out to everybody.
Super. Thank you. I think we're all in time for our next session. Thank you, Jeff. Appreciate it.
Cool. Thank you.
Tanzim, can you show the next talk session? I think it's Andrew. Can you open the slide? Okay. So, Ginger, do you want to introduce or you want me to introduce? I'm not sure Ginger is there or not, maybe. Okay, the next session is vendor perspective on addressing challenges with OT security in CI by Andrew Ginter, Waterfall Security. Andrew has been a great, strong supporter for you in these events. So thank you, Andrew, for all your continuous support and generosity of sharing your books and everything. We are very grateful. At Waterfall Security, Andrew leads a team that works with the world's most secure industrial enterprises. Before Waterfall, he led the development of high-end industrial control system products at Hewlett-Packard, of IT/OT middleware products at Agilent Technologies, and of the world's first industrial SIEM at Industrial Defender. Andrew is the author of 3 books on industrial or OT cybersecurity, co-hosts the Industrial Security Podcast, and contributes regularly to industrial security standards and best practice guidance. Andrew, it's a great honor to have you as part of the summit. The floor is yours.
It's an honor to be here. Thank you so much for the opportunity. Let me bring up my own slides. For a vendor perspective,
it's coming. I think you got frozen or something. I can't do. Tanzim, do you know what's going on?
No, I think it's
Oh,
back.
okay. Andrew, can you try again? Andrew has
yes,
got
I
a
will.
screen.
I will. One moment. I'm going to switch internets. My apologies.
Tanzim, can you download that catalog that Jeff
Yeah,
has
I
shared?
already downloaded it. I have
Thank
it.
you.
One moment. Okay, testing, testing. Is this better?
It's not yet
Testing.
showing up.
I have not started sharing yet.
Oh yeah, the your voice is good. Yeah.
Okay, okay, then let me share. And we'll try this again. How's that? Testing, testing. Testing,
It's
testing.
coming. Yes, yes, it's coming. Yes, you're good.
Okay.
Proceed.
Tell you what, I'm going to go off of video and maybe that will help a little bit. Okay, so as you heard at Waterfall, the last 15 years, I have the opportunity to work with some of the world's most secure industrial sites. I have the opportunity to learn what they do. And I've had the opportunity to write about what I learned in a couple of books. So I'm grateful for that. I wanted to comment. Dr. George Shea earlier talked about the word secure. One of the early things I learned is that there's no such thing as secure. Okay, security is a spectrum, just like safety. You can always be more secure. You can always be less secure. You can always be more safe. You can always be less safe. One of the things I observed in the first book was the only people who should be using secure as an adjective is people who sell stuff. How do I know this? All of my career, I've sold stuff. Who invented the phrase secure by design? In my understanding, it was Microsoft back in the days of, Windows NT and earlier when they were criticized so thoroughly for being so horribly insecure. They said, well, we need to fix that. So they invented a design process and they said, what are we going to call this? Let's call it secure by design so that everyone says, oh, now you're secure by design. Therefore, having used secure by design, you must be secure. Secure is a word that vendors use to try and persuade the population. How do I know this? I'm a vendor. Okay, see if you can catch me using the word. Secure is not a word that owners and operators or that governments should ever use. Security is, a useful word. The question, are you secure, is meaningless. The question, how secure are you, is a meaningful question. The question, how secure should we be, is a very important question. But there's no such thing as secure boot. There's no such thing as secure by design. There's no such thing as a secure system. So I agree completely. That said, let's talk about security. The history of a brief history of OT security that again, I've been either watching it or a part of it since the beginning in about roughly 02, 03. The first generation of advice that came out there, as I said earlier, back in the day, the early days of the initiative, who did we have that we could call upon to help write OT? Back then it was called SCADA, or it was called industrial security advice. We had IT security experts. In IT networks, 9 times out of 10, information is the asset. And so these experts came over, and the first generation of industrial security advice read like IT security advice, saying information is the asset, protect the AIC, protect the CIE of the information, encrypt everything that you can. It was much better than nothing. I'm not saying, I don't mean to criticize the first generation. That language is still with us. A lot of people still use that language. It's persisted to this day, but it's incomplete. The second generation advice started talking about physical operations as the asset, safe, reliable, efficient operations as the characteristics that we're trying to protect with a security program. In these, cyber sabotage being the risk that we need to address. prevent and observing that all cyber sabotage is by definition information. And so, and all information flows can be proven mathematically to be able to encode attack information. And so all incoming flows, both online and offline, are potential attack vectors. Looking at information as the threat, not instead of the asset, as a threat as well as an asset. Okay, we're not saying the original description was entirely wrong. Looking at it as both threat and asset was the second gen. Talking about sometimes we have to protect the information, it's trade secrets. Sometimes we have, most of the time we have to protect from information as well, because that's cyber sabotage. The other thing that became clear in the second generation is that the essential difference between IT and OT networks is consequence. Consequence defines the difference. A lot of the other differences, it's hard to patch. It's hard to, use even passwords on some systems. It's just hard to do some kinds of things. A lot of this is because of the consequence. The engineering change control discipline is how we manage a lot of risk in high consequence operations. Every change that we make to an operation is, risks, errors, and omissions. And so to prevent errors and omissions with unacceptable consequences, material consequences, we have to control change. We study the change. We practice the change. We document the change. The more consequential the system, the more of this engineering work we have to do before and to an extent after the change. This is part of why we have to manage some OT systems very differently from IT systems. The third generation, and this is within the last 5 years, the third generation of advice, the the word resilience has featured prominently in the advice. Until very recently, so what is resilience? It's defined as, the ability to rebound. I mean, a spring is defined as the stereotypically resilient object. You put it under pressure, and then when you relax the pressure, it returns to its original shape. We need our automation systems to be resilient. When they come under pressure from a cyber attack or any other cause, they might sort of compress into a less efficient mode, a less effective mode, but still effective enough to fulfill our mission to the organization, to society. And then when the pressure is released, the attack, whatever the condition is resolved, return easily to a normal state. This is the textbook definition of resilience. For many years, though, resilience was more of a headline than a recipe. What does this mean? You would say, well, resilience. How would you deal with the risk of bricking a PLC, erasing the firmware so thoroughly that you can't use the PLC anymore? You can't load firmware back into it. You have to throw it out. Oh, make the PLCs unbrickable. Every question you ask had a pat answer, but nobody could say, here's the recipe, start here and there. Now you have a, in quotes, resilient system. Resilience is also a spectrum, a more resilient system. It was only very recently with the Cyber-Informed Engineering Initiative that we have started to turn resilience from a headline into a recipe. What is cyber-informed engineering? You've heard many definitions. The one that I like, the textbook example I like, is the example of a boiler. If each of us is a technician in an old school power plant and responsible for 6 massive boilers, we're thinking, 5 stories tall and as big around as a bungalow or more. If we're the technician that calibrates the instrumentation, that replaces the instrumentation when it fails, that has the X-ray and the gamma ray, in situ corrosion detection equipment, so we don't have to shut anything down. If we worked 8 hours a day within the kill radius of a worst-case boiler explosion, how would each of us prefer to be protected from a cyber attack that overheats the furnaces under our boilers? Would we prefer a longer password on the PLC controlling the furnaces, or would we prefer a spring-loaded pressure relief valve, no CPU, unhackable? It mechanically opens when the steam pressure is too great and releases the steam. The experts say, Andrew, you're trying to deceive us. You're asking us the wrong question. They say, if I were that technician, I'd want the overpressure relief valve. I want 4 of them on each of my boilers because these things fail. Okay, there's corrosion, there's metal fatigue. I need at least 1 of these valves on each of my boilers to work to save my life when I need my life saved. And I want the longer password on the PLC. And I want a boatload, an absolute boatload of cybersecurity on the side because this is my life on the line. And this is, in a sense, the right perspective. Cyber-informed engineering is defined formally lots of different ways. I define it informally. I didn't invent this. I repeat it. I forget where I got it from, but it's a coin with 2 sides. One side of the coin is cybersecurity. Teach engineering teams about cyber attacks and how they work. Teach them about cybersecurity tools and each of their limitations so that we can evaluate residual risk. Teach, on the other side of the coin, is engineering. Teach IT teams about engineering change control. Teach them about overpressure relief valves. But here's the thing, the deceiving you with the wrong question. I want the overpressure relief valves and cybersecurity. When you spend a coin, which side of the coin do you spend? We spend the whole coin. We need the whole coin. We're not choosing one or the other. We need it all, and CI is the big umbrella. Elements of safety engineering are in there, elements of protection engineering, elements of automation engineering. Most of cybersecurity is all under the big umbrella. Manual operations as a fallback. Where is manual operations as a fallback in the ISO 27001 sort of universally used IT security standard? Not a mention of it. Where is manual operations in the NIST cybersecurity framework, the grand compendium of everything cybersecurity? There's not a hint of it. Where is it in the industrial 62443? To my knowledge, it's not mentioned. These are cybersecurity standards. These are sort of what the industry has relied on for the last, for 15 of the last 20 years before cyber-informed engineering started coming on the scene. They're not wrong, but they're incomplete. Cyber-informed engineering is, for the first time, creating the closest thing we have to a recipe, creating a body of knowledge, assembling the knowledge in one place so that we can use it to design resilient systems. And the essential difference between a lot of these manual operations as a fallback or the overpressure relief valves, the difference between these engineering grade and IT grade solutions is this. Engineering grade solutions are deterministic, and they work no matter what kind of cyber attack is coming at us. What's the opposite? What's IT grade? Let me give you a different example. Imagine that the engineering profession has figured out how to build bridges at 1/3 the cost of today's bridges with, I don't know, carbon fiber, something like this. Imagine that the 1/3 massive savings. Everybody wants to build bridges this way. The problem with the new design is resonant frequencies, harmonic frequencies. Anyone who's got as much gray hair as I do remembers the Tacoma Narrows disaster, the world's first really long suspension bridge. If you're not familiar with it, you can Google it. There's a video, watch the video. The engineers of the day had not figured out how resonant frequencies interact with the bridge design. A stiff breeze came up and started the bridge oscillating at one of its resonant frequencies. The bridge tore itself apart. It's there in the video. Imagine that the new design is riddled with harmonic or with resonant frequencies. People walking across the bridge are going to start the thing oscillating. People dancing on the bridge, forget it. The bridge is a goner. And so the design engineers have I've designed into the bridge active hydraulic dampers, multiply redundant hydraulics, multiply redundant power supplies, multiply redundant control systems, and AI controls the whole thing. The bridge feels rock solid because of the active damping. How happy would each of us be driving across that bridge to work every day if we knew that the design engineer hoped that if a cyber attack targeted the automation for the bridge, hoped that we could detect the attack before the bridge tore itself apart? How happy would each of us be driving across that bridge to work every day if we knew that the design engineer hoped that if we detected the attack in time, we could scramble an incident response team fast enough to prevent disaster? Hope is not what we expect of design engineers. We expect bridges to carry a specified load in a specified operating environment for a specified number of decades with a large margin for error. I asked a design engineer, how do you know the maximum load for, this pedestrian bridge over here? I showed them a pedestrian bridge. They said, Andrew, that's easy. You design barriers onto either side of the bridge so that you cannot drive vehicles onto the bridge. The load on the bridge is people. Most people are less than 2 meters tall. Most people are made of water. You model 2 meters of water, the width of the bridge, the length of the bridge. That is your maximum load. Design the bridge. He says, design the bridge to carry 8 times that load. You put an 8 times margin of error into the calculation because these are people. Failure of the bridge under load is unacceptable. And so this is the difference between an IT grade and an OT grade solution. An engineering grade solution. Increasingly, when we design automation systems, we are required to design systems that will carry a specified threat load until at least the next opportunity to upgrade. And we know these opportunities come at long intervals in engineering change controlled systems. Carry the specified threat load until the next opportunity to upgrade with a large margin for error, because we might have made a mistake in terms of evaluating the threat load that's going to be presented to the bridge. This is increasingly the expectation. This is the engineering perspective on security. This is the engineering perspective that's reflected in the Cyber-Informed Engineering Initiative. And don't get me wrong, I'm not saying don't do detect, respond, and recover. We need detect, respond, and recover. If there's an attack on an automation system that does not kill us outright, we need to be able to respond to the attack and kick it out and bring the system back up. That is the definition of resilience. But detect, respond, and recover is not enough. We need it all. We can't choose one side of the coin or the other. We need govern and protect, depending on what you call it, and the identify, detect, respond, and recover pillars of the NIST cybersecurity framework. Going a little deeper, a piece of CIE that I'm particularly interested in, and I featured in my most recent book. By the way, the book is my latest work. Owners and operators, practitioners in the field can request free copies. Waterfall distributes them for free. Mere mortals, students. My email is on the end of the presentation here. Send me an email. I'll get you a free copy. But the Waterfall marketing won't. So reach out to me directly. A piece of the CIE puzzle that I'm particularly concerned with is network engineering. What is that? Well, what happens when the overpressure relief valve engages in our boiler? Well, the steam escapes. Nobody dies. These are good things. And 99 times out of 100, the operator lifts the cage on the big red mushroom button, hits the button, and shuts the plant down. And in doing so, we've impaired national security. National security, where did that come from? The legal definition of critical infrastructure, and all large power plants are critical infrastructure. The legal definition of critical infrastructure is critical to the nation. How do we prevent impacting national security? We need to prevent the downtime in the first place. We do need to minimize the downtime, but we need to prevent the downtime as well. Network engineering is defined as deterministic prevention of the propagation of attacks pivoting through consequence boundaries. Consequence boundaries are defined as connections between networks that have dramatically different worst-case consequences of compromise. Oh, and I forgot something. Coming back to here, when I show this slide, and I've shown this slide to a lot of owners and operators in industry, in heavy industry primarily, the nearly, not universal, but the nearly universal reaction is, what a good idea. This makes sense. It's the same puzzle pieces we've been working with for the last 15 years, but you've put them together. CIE puts them together here in a way that has no space between the pieces anymore. There's no more gaps. You've eliminated the gaps. This makes so much sense. They say, this is great. And then they look at me and say, Andrew, why is this new? This should not be new. This should be how we were looking at the problem from the very beginning. But it isn't. It is new. So, in my opinion, cyber-informed engineering is the biggest, the most important change to happen in the world of OT security. Since the Gartner Group coined the phrase OT security in 2005. So, cyber-informed engineering, network engineering is deterministic prevention of attack information pivoting through consequence boundaries, through connections between dramatically different kinds of networks. The networks may use the same technology, but they are managed differently. They have different functions. Some examples of network engineering. And if I may, another reason that network engineering is becoming increasingly important is because while we talk about overpressure relief valves, we talk about analog safeties, we use analog safeties, many industries are moving away from analog safeties. And you might say, oh, well, why are they doing that? It's because the analog safeties are cheaper. Well, in a sense, they are. Analog safeties tend to be cheaper than, digital safety instrumented systems tend to be cheaper than analog safeties. The digital safety instrumented systems will report, or you can detect their failure more readily than you detect corrosion in an analog safety. The digital safeties are generally more easily repaired than the analog safeties. For all these reasons, yes, the digital safeties are cheaper than the analog safeties, but what this means is that we can deploy more of the digital safeties. Arguably, the digital safeties are safer than the analog safeties as long as we ignore the cyber threat. And so network engineering is one way to address the cyber threat, to address the risk of bad stuff leaking through consequence boundaries. The network boundary around an around a digital safety is always a consequence boundary. We need to prevent the bad stuff getting in if we're going to benefit from digital safeties in an all digital world. And this is, to a large extent where we're going. Some examples, the EPRI industrial internet methodology. EPRI is like Idaho National Laboratory is hundreds of PhDs that are, do research for hire. EPRI was tasked some years ago with figuring out how to do vibration analysis, predictive maintenance on steam turbines with industrial internet devices without incurring unacceptable risk, without the risk of an attack pivoting through a cloud-based preventative maintenance provider into the control network and misoperating the turbine so thoroughly you destroy the turbine. The answer that came back is it's actually straightforward, conceptually at least. Get one of the vibration monitors. Take them apart, do an engineering study, prove to yourself that these industrial internet devices, cloud-connected devices, that they are truly monitor only, that they are physically incapable of controlling the physical process, the steam turbine. Connect these devices to the turbine, connect the network ports on these devices to a DMZ on the IT network. Connect that DMZ out to the cloud so that the vendor can monitor the devices and tell us how to maintain the devices optimally to reduce our cost of operating the devices. This is predictive maintenance. The answer came back, do the engineering study, prove that they are monitor only, connect them out to the world, do not connect them to the control network in the power plant. In that configuration, what is the worst that can happen if the bad guys compromise the vendor cloud and pivot through the cloud into the devices? What's the worst that can happen if they reach the devices somehow on the internet and compromise them directly? Well, you can send bad information into the predictive maintenance system. You can get bad advice for maintaining your system. It can cost you, $3 million a year more to maintain the turbine than it would otherwise have cost you. But you cannot destroy the turbine, because even if you take over the firmware in the device, you have gained no advantage in terms of getting into the control network where you can miscontrol the device. Clever. Physically separate network. They said, sure, connect that out to DMZ on the IT network. Sometimes just stick a SIM card in the device, because they take SIM cards, put them straight out on the internet. The worst you can do is suffer a few $1 million loss. You can buy insurance for those kinds of losses. Nowadays, it is practically impossible. It's not quite theoretically impossible, but it's practically impossible to buy insurance to replace a $500 million steam turbine that's been destroyed by a cyber attack. You can't do that anymore. Another example is analog safeties. A lot of us have safety instrumented systems, and we want to be able to monitor these systems. If one of these systems fails, we need to know, the operator needs to know right away that it's been failed so they can schedule a replacement. These things are important. We need to keep them working. Even if there are redundants, we want to promptly fix the primaries that have failed. How can we monitor the safety system from the main HMI without risk of compromising the safety system? All information flows, all TCP is bidirectional, all information flows can encode attacks. Use analog signaling. 4 to 20 milliamp current loops can send an analog signal. You can send a heartbeat, a 1 or a 0. I'm alive. I see I'm heart beating. If my heartbeat stops, you need to come replace me. I'm dead. Send a status. I'm tripped or I'm not. I have 300 safeties in my plant. If the plant goes down on a safety, I need to know which safety took the plant down. I need to know why the plant went down. These safeties are not that complicated. There tend to be between, 20 and 200 reasons in the safety that it can shut the plant down. Well, that the accuracy of a current loop is easily 12 bits. You can encode a number between 0 and 200 in a 12-bit accuracy on a current loop. Here's the thing, you can monitor the safety through these current loops. Turn off the HART protocol, which is messaging over the current loop. You can monitor the safeties, but I defy you to pivot a cyber attack through these monitoring interfaces into the safety system and reprogram or otherwise compromise the safety system. So this is another example of deterministic prevention of attacks pivoting into high consequence systems. By far the most frequently used system for network engineering is the unidirectional gateway. NIST defines it as a combination of hardware and software. The hardware is physically able to send information in only one direction. The software makes copies of servers. So the hardware is, think 2 circuit boards, a laser on one side, a photocell on the other. You can send from one side to the other, but nothing can get back. The software makes copies of things. If we have an Oracle database, a Pi server, an OPC server, a Modbus device on the industrial network, the software connects to the device back of the envelope. It's more complicated than this, but back of the envelope once a second and says, give me everything new, and takes that snapshot of data and pushes it out to the enterprise network. And on the enterprise network populates an identical server. If it's Oracle on the inside, it's Oracle on the outside. And now anybody on the enterprise network who needs the data can ask the industrial network for the data and gets the same answer as the live, sorry, can ask the enterprise server for the data and gets the same answer, give or take a second, the same answer as the live system would have given, um, without ever needing to send a question or any other information back into the OT network that might contain an attack to compromise the network. So most common design for network engineering, but far from the only one. And this, if you get a copy of the book, is chapter 5 in the book. I'll look under the hood again, 2 circuit boards. I'm running short on time. I have a new book coming out in the spring. Stay tuned, connect with me on LinkedIn. And the book is looking at the future of the cloud. The cloud is coming everywhere in the industrial internet, in the industrial automation world. Increasingly, the cloud is making safety critical decisions. How can we do a safety critical cloud? Network engineering features prominently. Let me give you just one example. I mentioned it, which is an independent safety backstop. If we have a cloud service that is sending instruction into the industrial control system to optimize something, complex problems are being solved in the cloud. Optimization is generally a hard problem. Sends instructions in. What if those instructions have been tampered with? What if the cloud service has been tampered with? What if it's instructing our system to destroy itself? Independent safeties, independent protective relays. If we have a safeties make very simple decisions. They ask the question, is the system safe right now? Is it safe enough? Is it operating in a safe mode? And if the answer is yes, it continues. If the answer is no, triggers an emergency shutdown. Answering the question, is it safe, is much simpler than answering the question, how do I optimize? Let the cloud do the hard stuff. And if the cloud is ever compromised, or the AI in the cloud just messes up and sends really bad instructions to us, our internal independent safeties save us. But they must be independent, not just from electrically and software-wise. They have to be independent cyber-wise with respect to cyber attacks. You cannot have a single cyber attack that will take out both the cloud system, the control system, and the safety system. So this is a very old concept, a very old design. But everything old is new again. Use this very old concept from engineering, and we can reap the benefits of the cloud without suffering the risks. Real quick, something else that is, in a sense, bleeding edge that people are debating right now is how to communicate risk, how to talk about risk with business decision makers to get our budgets approved so that we can make things secure. The universally used approximation for risk is that risk is impact times likelihood, but it is an approximation. The problem with this approximation is that people use qualitative metrics. Very low is 1, very high is 5 on both impact and likelihood, and the math does not work. This is a well-known problem. We defend a small shoe factory from people clicking on bad links, high frequency, low impact events. We defend that very differently from a high-speed passenger rail switching system, where the worst case consequence is trains collide, mass casualty event. The adversary that we worry about is nation state, or sometimes nation state grade ransomware. We defend these two systems, against these two risks very differently. But the math, the qualitative math, is the same. It says they're both low risk. They deserve the same degree of protection, but that's just not true. What we see in practice is that a lot of practitioners use likelihood and frequency for low impact events or lower impact events. For high impact events, likelihood is ignored. And we use the legal requirement in many industries is to use the strongest, reasonable, practicable protection. This is the legal requirement up here. But the formula that we use, the word likelihood muddies the waters because cyber attacks are not random. If a nation state takes down a shoe factory, or forget nation state, if nation state capable ransomware, the high end of ransomware has become indistinguishable from nation state. If high end ransomware takes down a shoe factory and we restore everything from backup, it takes two weeks. We pay through the nose to the gurus who come in to do the work. Insurance pays us all back. If we change nothing, because, likelihood suggests that attacks are random, randomness, it was just bad luck that we got hit. What's going to happen? A month later, we're going to get hit again. We're going to go down exactly the same way. Cyber attacks, many of them, not all, many of them are more deterministic than probabilistic. Targeting at the high end is deterministic, not probabilistic. A nation state will go after a target. The team tasked with that target will go after that target until they succeed in their mission objective or they're given another target. Okay, they're not opportunistic. So a lot of reasons that likelihood is the wrong word. What we're seeing people moving towards, and you're not going to see this in the standards and the guidance for another year or two, but this is early days. We see people using the word credible. When we make decisions about other people's safety, we have a legal obligation to make reasonable decisions. Credible is defined as what is reasonable to believe. And with the word credible, we can say, fine, we're doing frequency and impact on the low end of the risk scale. That's the easy advice. What we need is advice to become more useful on the high end of the scale, where we can ask the question, what attacks do we defeat reliably? What attacks do we not defeat reliably? There's a line between those hypothetical sets of attacks. And then we have to ask, are any of the attacks that have unacceptable consequences that we do not defeat reliably, are any of those attacks credible threats, reasonable to believe will come after us in our planning period? If there are, what are we going to do about them? We either need a very senior person to sign off accepting $1 billion in potential risk, or we need a budget to fix the problem, to increase the strength of our defenses so that we can reliably defeat these credible threats. So this is something that you'll see coming in the next year or two. This is currently being debated. This is 2 or 3 chapters out of my new book. I've run out of time. Let me say just one more word. I work with a lot of owners and operators, and I see blind spots. And so something we have to be aware of going forward is it's not enough to say, evaluate the consequences if we're blind to some of these consequences, to some of these scenarios. Safety instrumented systems are software. And if they can be reached by a pivoting path, they can be compromised. Protective relays are software. Same thing. Protective relays protect equipment. Safety protects human life. If we erase the firmware in 80% of the PLCs in our power plant, in our factory, in our infrastructure, do we have enough spares? Usually not. Will the vendor sell us spares? Usually not. This is 10 years into the life cycle of the system. You can't buy those PLCs anymore. So beware of blind spots, and summing up. Information is an asset. It's not the asset. Yes, we need to protect the information, and we also need to protect from information deterministically with network engineering if we can. And we need to detect, respond, and recover. Detect, respond, and recover addresses a different piece of the threat puzzle than does prevention. We need prevention and detect, respond, and recover. We need both analog and digital defenses as well as cyber defenses. Cyber safeties, the cloud is the future. We have to address the risks of the future as well as the risks of the present and the past with analog stuff. So this is what I had. My email here, if you'd like a free copy of the book, send me. I might have time for a question. I might not. Ginger, how am I doing?
You have time for several questions.
Okay.
I think we want to take a few questions from the chat and then also give folks a chance to take a quick break before we start the next section. So I was going to ask you, you have spent a lot of time looking at threats to critical infrastructure systems. And in fact, one of my favorite yearly publications from Waterfall is that yearly threat report. Can you summarize what you're seeing in that report and what advice you have, especially if you're pulling this year's information together? I'd love at least a snapshot of what you're seeing, even as we're going through this year.
Absolutely. So the report, the word attacks is in the report title. I'm thinking next year we need to change the word to breaches, because we're not tracking attacks, we're tracking breaches. We're tracking failures of cybersecurity programs in the face of credible threats. We track breaches that had physical consequences in heavy industry and the critical industrial infrastructure in the public record, no private disclosures. I'll just wave my hands. What we observe is that for a decade, that list of events was reasonably flat. We're talking between 0 and 5 events per year, breaches per year. At the turn of the decade, 2019, 2020, that changed, and it shot up to about 75-ish, 70, 80-ish, and it's been bouncing around between those limits for the last couple of years. We have seen, I thought initially this was an exponential increase, but really it was a step function. The data from 2025 so far is looking to validate that we've plateaued at about 80 breaches per year with physical consequences. Most of those breaches are ransomware. We observed that there's 3 ways that ransomware can affect physical operations. One is abundance of caution. This is the colonial scenario. Bad stuff gets into IT. It cripples the IT systems. And because we're not confident of the strength of our OT security programs, because we're operating a safety critical process, we shut it down until the mess in IT is looked after. This is roughly 1/3, 1/3, 1/3. The second third is dependencies. The textbook is Maersk Shipping. When the world's largest container shipping company got hit by NotPetya, the IT network was wiped out. The ships were unaffected. Okay, nothing got into OT, just like Colonial. Nothing got into OT, but still we were shut down because the ships could sail safely into port. Okay, their OT systems, their navigation systems were unaffected. The cranes could lift the containers off the ships. They were unaffected. But when we tried to log into the IT network and print a waybill for the truck driver, I'm sorry, we couldn't get into the container tracking system. We had a dependency on an IT resource. It was not safety critical. It was reliability critical. So that's a second aspect of network engineering, is understand our dependencies. And the third is, of course, the bad stuff gets in, encrypts the HMI, and so we have no choice but to shut down. So this is sort of the headline takeaway, but there's a lot of other sections talking about living off the land attacks, talking about GPS spoofing has become universal in some parts of the world, the parts of the world that are affecting the, near the Ukrainian Russian conflict, the Russian invasion. And there's other stuff happening in the world. The big news recently, of course, was the Jaguar Land Rover breach that might have broken the record for the most expensive breach in history. It used to be Merck Pharmaceutical, which again was NotPetya. They filed a $1.3 billion insurance claim with Zurich when they had to shut down 4 plants and throw out all of the batches in progress. Some of these batches are very expensive. Jaguar Land Rover looks like they've got a line of credit in the name of $3.5 billion to help them recover from this breach. Are they going to spend it all? I don't know. I don't know what the final number is going to be, but it looks big.
I'll say one of the saddest things about that cyber attack, but one of the things that hit home to me the most was that cyber attack affected not only Land Rover, but it affected the suppliers, some of them very small UK businesses that we think, bucolic environment, lots of support for workers' needs. And in this case, the best advice they got was, you are going to have to accept government assistance to feed your family because Land Rover can't pay you and there's nothing we can do. And that kind of from the business to the kitchen table is something I haven't seen in a breach. yet. And that really brought that home, and especially at almost a country level. We've got a lot of, oh, go ahead.
I was just going to say there was a degree of that back in 2020 when the ECANS malware hit Toyota. I think it was 4 plants went down for 2 days each, and again all of their supplies. But it was 2 days. It was not a month and a half like we have here.
We have a lot of students on this call and some professors. Other than your always generous offer to request your books, what advice do you have? Because some of the things that you talk about and I talk about are very nuanced, and it's hard for someone at the beginning of their understanding of engineering and cybersecurity to really take advantage of it. What advice do you have for them?
I gave some of it already, which is do use the opportunity to study attacks. Attacks, in my experience, are underemphasized in training programs, and there's a lot to learn on the defensive side. Yes, the reason I got so much out of the at the time it was DHS, the ICS cert. Today it's CISA, the 301 course, was because it was the first time I had been exposed materially to attack techniques. And again, ever since I've been able to evaluate defensive designs against attacks. One of the white papers that you can download, Google top 20 cyber attacks on industrial control systems. You'll find the white paper. And if you don't, send me an email. I'll get you a copy of it. And it gives, it's a spectrum of attacks across the spectrum of sophistication, so that you can look at a defensive posture and say, I'm dealing with this one, not that one, but this one. And then you can use that ruler, the red-green ruler, to look at a different defensive posture and say, how does this compare? Is it materially different? So if I say anything in hindsight, though, when I wrote that paper, I was focused on preventing attacks. It does not reflect really the value that the detect, respond, recover pillars bring to us. So that's a nuance that I'm still working on in my next work. But there is that. Any other? I guess the other advice I'd give people is when you look at the field, two things. And there's some hiring advice as well. The field is broad. Okay, the skills that you need, the training that you need to be a security analyst in a SOC is very different than the training you need to be a pen tester, is very different than the training you need to go and touch industrial systems and apply security updates to them, is very different from the training that you need to design a security program. Okay, these are different levels in the organization. Some of these are technician roles, some of these are engineering roles. These are very different skill sets. So when I was a young man, I never got career advice. It never occurred to me to ask someone for advice. I thought I knew everything. See, I would encourage people to get career advice from someone who understands the spectrum of security, and figure out what to specialize in, at least for the first few years of your career. And do specialize in it. Start now. When I hired people, one of the things I looked for was a pet project. The pet project might be a game. Have a pet project. Do something that interests you. Because if I could hire someone whose pet project, a game, how does a game work? Well, I've got, RS-232. We got 3 machines talking to each other. People are a little sheepish about that. I'm writing RS-232 communications drivers. Okay, I need these skills. And here's the difference. It's a difference between skill and talent. Skill, you learn. You study, you learn, you acquire the skill. Talent is not what you're good at. Talent is what interests you. And if there's something that interests you, pursue it. Get better at that. You will naturally drift into roles where you use the skills, you use what you've developed that interests you, because you naturally get better at it. You're interested in it. You spend some of your spare time thinking about it. I would always prefer to hire someone who provides evidence of talent as well as skill. Let me leave it at that.
I love that advice. I think sometimes, especially those who talk to a lot of different people, are discouraged from geeking out in a conversation. And sometimes when someone finally geeks out with me and opens up what they're looking at, and I can see their thought process and how deep they're willing to go with it, that's the time when I could make an employment decision of, if they're willing to go deep on that, if I'm paying them, what are they going to be willing to go deep on for me?
That's right.
Thank you for being with us today. I always appreciate having you brief and your advocacy of cyber-informed engineering. I look forward to many, many more conversations like this.
Thank you so much for the opportunity. I hope it was useful to you and to the listeners here.
Wonderful. Thank you, Andrew.
My pleasure. Take care.
Bye-bye. For those joined to the meeting, we are going to take a brief break, load up some slides for our next presentation, which will be a cyber-informed engineering workshop. We've talked a lot about cyber-informed engineering today, and this is our opportunity, admittedly on a Thursday afternoon, to dive deep into the subject. So before I strap everyone to their chairs and subject them to 2 hours of us being very enthusiastic about this topic, I thought it would be a great idea to take a quick break, allow everybody to check email and do any other function that is necessary, and come back here at 1:15 Central Time. So I will see everyone back here at 1:15 Central Time. As a note to those who are joined from the website, who may be taking advantage of the ability to pause and play, for this training, if you would like to hit the join button and come fully into the webinar, that will give you extra opportunities to participate. But if you want to lurk on the website, you are also still welcome to do that. Okay, see everybody at 1:15. Good afternoon, everyone. Our final presentation for today is on cyber-informed engineering. This is a workshop for establishing a cybersecurity lifecycle that enables thriving in a contested space. I'm Ginter Wright, and I'm the Cyber-Informed Engineering Program Manager for the Idaho National Laboratory. I've gotten to speak to you quite a bit here this week, and I've enjoyed it. I'm joined by Jeremy Jones, who is a critical infrastructure security analyst for the Idaho National Lab. At INL, Jeremy focuses on research and development targeted to securing the nation's critical infrastructure, primarily in power grid technologies and some exposure in AI. Jeremy's career focus has been on validation and verification, test and evaluation capabilities for emerging power grid technologies. More recently, he has focused on cybersecurity and cyber-informed engineering approaches to securing emerging grid supporting technologies such as generative AI for monitoring, management, and control of energy systems. Prior to joining INL, Jeremy was the testbed architect and operations lead for the critical infrastructure cybersecurity testbed and the cyber physical experimentation environment for research at the Information Trust Institute at the University of Illinois, Urbana-Champaign. Jeremy, thank you for joining me. And I should be sharing a set of slides. As we talk about cyber-informed engineering, we must acknowledge that we are in a contested environment. Where we could have at one point assumed that the cybersecurity capabilities that we leverage for defense by themselves are sufficient to keep adversaries out, we learn daily that that is not the case. As Andrew discussed with the Land Rover incident quite recently, adversaries can have immense impacts on our operational resilience beyond just our data. Before I go deeply into cyber-informed engineering, however, I wanted to talk a little bit about the Idaho National Laboratory. I wasn't sure if everyone in the audience had heard of Idaho National Laboratory or had good understanding of what a national lab is and does. So Idaho National Laboratory is one in a network of 17 Department of Energy national laboratories. We are DOE's lead lab for nuclear energy. And as you might imagine, things on our site campus are very, very busy right now as we are working with lots and lots of small modular reactor vendors, trying out many different designs and capabilities for energy dominance. We are also a major center for national security, particularly in industrial control systems cybersecurity. I've got some metrics on this slide that give you a sense of our size and the budget that we operate under. The Idaho National Laboratory performs research in the national interest that maintains America's competitiveness and security. INL's national and homeland security focus areas include industrial control systems security. We've talked about that a lot this week. A secure and resilient grid, wireless security. We perform first responder training, particularly helping first responders that may respond to events where radiologic material are part of the response environment. And in those environments, we help train those responders so that they can be safe even in an environment with radiologic materials. We perform research on nuclear safety and security, ensuring that both our commercial and research reactor fleet are safe from physical and cyber incursion. And finally, we perform support to national defense. INL is unique in that we have an 890 square mile site that is almost the mirror image of the outline of our state. You can see it here. It is also about the size of Rhode Island. And that provides an excellent place for experimentation at scale. We have an electric grid test bed with full-scale electrical equipment, including transmission and distribution scale assets, so that we can test out the challenges and the defenses and mitigations that our asset owners need. We have a water security test bed that allows us to test threats to the water system and mitigations against those. We have radiological ranges, as I discussed, that let incident responders detect and recover radiological materials safety. And a little bit later in our lecture, I'll talk a little bit more about how that happens. It links into cyber-informed engineering in some interesting ways. We have what we call the specific manufacturing capability, and I love the Department of Defense for their very vague but specific project names. In the specific manufacturing capability, INL creates the armor for the M1 Abrams tank. And that is that mission. We also have an explosives test range, which is a great deal of fun when they start setting off charges. And the focus of that is to ensure that the vault technology that protects nuclear fuels and other critical materials for nuclear purposes is as secure as we hope that it is. We have nuclear materials facilities, including facilities where we can do post-irradiation examination and scientific experimentation on material that has been irradiated. We also have cybersecurity and energy security laboratories. These labs are interesting because we can hook them to these test beds and get digital information about the at-scale activities that we take on. We also have a wireless test bed with full-scale tier 1 cellular equipment out in the desert where we can do wireless testing. All of these capabilities we can use individually or in concert to respond to the nation's needs and to create secure solutions for the challenges that we face. With that, INL is we are the most prepared for cyber-informed engineering because of our history. The Idaho National Laboratory, as the nation's nuclear energy laboratory, was charged originally to construct and test nuclear reactor designs. At the advent of the nuclear energy race, no one understood how to run a reactor successfully. What were the boundaries of safe operation, and how in an incident does one shut down the reactor effectively? INL was charged with coming up with those safety protocols, and in doing so, we had to instrument and test and cause failure in a number of different nuclear reactor designs and environments. In that endeavor, we learned a great deal about industrial control systems, about how to test to failure, and what failure looks like. And that experience directly applies to our approach to cyber-informed engineering. As we talk about cyber-informed engineering, especially today, I do want to say what we're going to cover this afternoon is a body of knowledge. I'm going to spend 2 hours with you poking with a flashlight in every nook and cranny of what we think about as cyber-informed engineering. If you like what you're hearing and you want to apply this material, there are ways to apply this that are a lot more straightforward and direct than what we're going to talk about today. Today is about a transition of the body of knowledge, but I'll show you as we go through the material some tools that will allow you to access this material so that you can specifically apply it to the challenges that you may encounter. So, together today we learn, but please don't be overwhelmed at how broad this material is. We simply want to show you the breadth of it and allow you that introduction. So first, before I talk about cyber-informed engineering, to make sense of cyber-informed engineering, we must first talk about what cybersecurity is. And we've done a lot of that conversation this week. We've talked about cybersecurity. I'm going to pull a definition from the Cybersecurity and Infrastructure Security Agency, CISA, that defines what they think cybersecurity is. And especially for the students in the audience, you will see sometimes how our definitions constrain our thinking. CISA says that cybersecurity is the art, first of all, we'll go on, of protecting networks, devices, and data from unauthorized access or criminal use, and the practice of ensuring confidentiality, integrity, and availability of information. After the exposure you've had of these 2 days, I hope that when you look at this definition, you see it as half of a definition. This is a definition of cybersecurity for information technology systems, where the key asset to be protected is data. The key threat to that data is a breach of confidentiality, data integrity, or data availability. But as you've heard our infrastructure experts, our power company and water company practitioners talk this week, I'm certain that you've seen that what they worry about, although they do worry about the confidentiality, integrity, and availability of information, they worry about that far less than they worry about the safety, reliability, and performance of their critical systems. And that is completely missing in this definition of cybersecurity. The Colonial Pipeline incident was brought up earlier today. In this incident, ransomware attacked a pipeline facility. It was focused on the information technology networks, and we have no information that suggests that it was able to penetrate past those. However, shortly after the ransomware was detected, Colonial Pipeline elected, out of an abundance of caution, to curtail pipeline operations, to stop sending materials through the pipeline. So the question that my colleague Joe Slowick poses is, if Colonial Pipeline was purely an IT issue, why are we thinking about it for operational technology? Why did Colonial have to stop all of their process and operational technology work just because their computer systems went down? And the answer to that is an interdependency issue. Andrew reflected on interdependencies in his talk. Colonial Pipeline had a file on their IT network that told them basically what products were moving through the pipeline and had the access instructions for customers. And that would ensure that if I were somewhere along the pipeline and I began to open the tap for my product, I didn't get someone else's jet fuel, I got the Kool-Aid that I was expecting. And this is a very important file because that manifest ensures that the customer is getting the product from Colonial that they asked for, that they're getting the amount of it that they wanted, and that the product has the quality and material expectations that the customers want. And without this file, Colonial recognized that they could not safely continue to operate their pipeline, even though every part of the pipeline was completely insulated from the ransomware attack. Colonial couldn't move forward because they had lost this one manifest. That will tell you how closely these systems are related and how, with a loss of data, a complete loss of operations might be experienced by a company. Colonial's issue wasn't the fact that they had the unavailability of the data. It was that the unavailability of the data led to a challenge of their ability to operate. To describe this more fully, I'm going to show you a graph that was developed by a different colleague of mine. It's got a lot of information in it, and we're just going to look at a few pieces of it. As we think about information technology, operational technology, and industrial control systems, and we've leveraged those terms over this week. Starting at information technology, the core features that we are interested in preserving with our security functions are, as CISA indicated, confidentiality, integrity, and availability. And depending upon the services that we need, we may reorder those words, but in general, we want to ensure that the data in our networks stays our data, that it is predictably appropriate and doesn't change form, that its integrity is intact, and that the data is flowing for the applications that need it. Often on an IT network, we have cloud services, we have web services, we have voice over IP, we host things like email. A lot of our business applications are conducted on the IT network. The focus is information processing, and typically it involves corporate level data. When we move deeper, closer to our operations, we get into our operational technology network. This is typically in a site or a plant. It has tools like SCADA systems, embedded devices, Internet of Things, and industrial Internet of Things. It may connect with a distributed control system. It may have human-machine interfaces. The purpose of the operational technology is to collect information about process operations that feeds our business processes. So this is not where the things get cooked or moved or transformed, but it is the place where we understand how many of them got cooked and what are the quality levels, and were there any that got sent back? What's the temperature on the oven or the pressure in, I always think of the Twinkie factory, so that's where my examples come from. So what's the pressure on the extruder that puts the cream into the Twinkie? That's the kind of data that is collected on an operational technology network, and it's made available to the business processes that then imagine the financial benefit of the products that we are producing. Typically, in an operational technology network, we take that confidentiality, integrity, and availability triad and we reorder it. Because when we have a process that's running, the most important thing is that the information about the operation of that process stays available. We want to know all of that information so that we can package the goods that we have, so that we can have the trucks ship them out, or whatever other distribution mechanism is important. We want the data to match the paradigm we set for it, and that's where integrity comes in. And finally, yes, if there are trade secrets in how we make the Twinkies or the donuts or the electrons, we want to keep those to ourselves. But the most important thing is the fact that that data is available. And you'll see that that data comes from the operational environment, and it typically does not go into it. This is logical data. Now we're going to go one more step deeper, and we're going to walk into an industrial control system network. This is the place where we have actuation, we have movement, we have stoves, we have transformers, we have process-specific systems that perform physical functions. You might find valves, relays, switches, signals, pumps, sensors, and safety equipment. All of this might be correlated and reported through a remote terminal unit or a PLC. This is where the moving parts are. And here on this network, suddenly the things that we find important change. The most important thing on an ICS network is safety, and that is a physical property. We want to ensure that the customers who rely on our products and the workers who work our processes are safe in the performance of their duties. We also want to make sure that these processes are reliable, that they feed the business's mission as we expect. And finally, we want to ensure that they perform, that our power is available 24 hours a day, 7 days a week, and we don't have unexpected outages. Same with our water and the other critical services that we depend on. So you can see as we go through this chart, as we move from operational technology to ICS, our priorities completely changed. We've moved from the digital world to the physical world, and the physical properties of the system are suddenly important. Likewise, as our adversaries move from the information to the operational technology into the industrial control systems, we have to protect the safety, reliability, and performance ahead of confidentiality, integrity, and availability. And I really love this chart because it just lays out all of the different paradigms for thinking about cybersecurity in an operational environment. Jeremy, would you like to add anything here?
Not much. I mean, I think that the important takeaway, right, is that as you get closer to the physical process, the physical machines and items that are doing the actual work, right, that safety consideration starts to move up and up and up and up and up to the point where it does become the most important thing. It's the first thing you think about in a physical process environment. And while the information is important, it becomes, information about that process, and it helps you run the process and look at and understand what the safety is, as opposed to, right, in the IT environment where it really is about the information. It's about protecting the information, ensuring the confidentiality of the information. And if your server goes down, you don't really have a safety issue. Like you would if, say, a valve or a relay or something like that misbehaves.
Thank you, Jeremy. Sorry, my screen locked there on me just a second. So I've got a real example. Andrew in his talk suggested that we could learn a lot by looking at infrastructure attacks. And boy, do I have a fun one for you to think about right now. So this attack is called Triton or Trisis, if you want to look it up in literature. And it was a cyber attack on a safety controller system, a safety instrumented system that was called a Triconix. And I've got a small picture of the larger box on this slide. The good news was the attacker was not successful. They were not as great coders as they were thinkers. And so their capability was found before it could have an impact. And that's good news. But as our labs started to take that capability apart, we learned something really interesting. This attacker had tried something that hadn't been tried before. To explain their attack, I've got to talk to you a little bit about how safety instrumented systems work, and in fact, how a whole lot of ICS devices used to work until fairly recently. As you can see from the image, this system has a key lock, and it allows and controls the system from being in a run mode, where it executes the logic that's available on the system, and it can be moved to a program mode if you have the key. You can also, and in the program mode, I can change the configuration. I can change all of the parameters that the system operates under. And the idea is that I would put it into program mode, I would update my configuration, whether I'm uploading a file or editing it on the screen, and then I would turn it to run mode. And I probably would have the key around my neck, like my little necklace, and I would be going about my daily job with my key on my neck, and no one else had the key but me. And that ensured that the device couldn't be put into the configuration state without whoever is trusted with the key's awareness. That key also controlled whether the device was in local mode, in which it operated, again, with just the logic that was available to it, or it was in remote mode, where it could be controlled by someone who was at a distance, perhaps the central office or wherever. All of this sounds like the basis for some really good security. In this case, when the attack capability was taken apart, they realized that this adversary had discovered that this key switch operated on memory. So that when I moved the key from run mode to program mode, I activated an area of system memory that then allowed the configuration screens to come up and those instructions to run. There was no physical barrier for the key. The adversaries realized, wait a minute, if you're moving this to a memory location, well, if I own the device, I can activate memory. I don't need no stinking key. And that is exactly what this capability tried to do, was move the configuration of the device into program mode through activating that memory location so that they could put new instructions in that would cause a safety issue with the process, and no key was required. Just a changing of the memory location that was behind this lock. One of the interesting things that we learned by looking at this was that anyone who was an engineer didn't even think about what was happening behind the key, didn't even have training, wasn't even in their brain to think, well, what's behind that key? What happens when I turn it? Is it a physical board that's activated that is truly a lockout? Or is it just software behind that key? And very dismayed most engineers were to find out it was just software behind that key, and the key wasn't really a safety device at all unless you were there in person. The remote adversary could push right past it, even if a local person used the key to do their business. If this group had thought about cyber-informed engineering, there could have been specific limits on how that function operated. It would not have been just software only. There would have been some physical actuation that happened so that someone with control of the digital system couldn't push a safety system to unsafe characteristics. Jeremy, anything you want to say about this one?
Sure. I was one of those people. For a long time, I was one of those people that would happily go around saying, see, if you just put it in run mode, you'd be okay. And it was quite an eye-opening experience, having the conversation. The first time I had that conversation around, how this is actually implemented in this particular system. We had one of these in our test bed, and we helped out with some of the private organizations that did some of the research on the Traces attack, and it was quite the eye-opening experience. And then you start thinking it really kind of changes the way you think about things, right? Because then you start thinking, you see these key switches all over the place, and you're like, okay, but is that really a key switch, or is it really just a physical interface to memory? And it really changes the way you start thinking about things and what the capabilities really are and how they're implemented behind the scenes.
And if you're curious, they did fix it. And just to remove concerns, later versions of the device don't have a key switch at all. So now it's just software. And we all know that because there's no key that takes our minds to the wrong place. So a great particular illustration of how software and digital technology has creeped into things that engineers are taught to think about as analog systems. So based on that, we believe that engineers are a missing piece in operational technology cybersecurity. Adversaries, as we've talked about a great deal this week, attack the digital domain. They go through digital pathways, including communications pathways and other things, to gain access to a network, to laterally move across it, gain capabilities, gain ownership over system or mission functions, and then to have an impact. The cybersecurity techniques that we put in the way of those adversaries, the ones that are digitally based, typically make it more difficult. We talked about earlier using encryption to protect data. Well, using encryption doesn't physically make it impossible for an adversary to do their work, but it does raise the difficulty level. If I have a router that manages communication pathways and only allows certain pathways to talk to others, again, it looks like I've made it physically impossible, but I've also just kind of made it more difficult. Now my adversary has to find a way in and take advantage, work within my limits to make their capability occur. When we add engineering controls, we can reduce the damage of an attack. So let's imagine that an adversary is able to penetrate the digital domain, move through our various defenses, and gain access to one of our process systems. Not only access, but control. If I have an engineering control as a mitigation on that system, even if they change what was 50 gallons of chlorine per hour into 5,000 gallons of chlorine per hour, a significant change, you'll agree. If the pipe diameter on that system is appropriately sized, even with 5,000 in the digital device, only 50 gallons per hour will flow through my pipe. That pipe diameter serves as an engineering control that limits the attack damage that an adversary can do. Yes, they have control of my system, and that's bad news, but the good news is they're manipulating various features that don't give them any impact at all. My system is safe because of the engineering I performed, as well as whatever digital devices made this attack difficult in the first place. By joining our cybersecurity controls and our engineering controls, we build defense in depth and create physical barriers for our adversaries. Anything here, Jeremy? Okay, with that as a background, now we can really talk about what cyber-informed engineering is. So cyber-informed engineering uses engineering design decisions and what we just talked about, engineering controls, to eliminate specific harmful consequences of an attack. This usually is applied at an engineering level. We want to think about what the worst case consequences are and put specific mitigations in place. Although cybersecurity experts can help with the application of cyber-informed engineering, and particularly can explain to engineers and technicians what digital devices might do that they may not have thought about, the mitigations are really focused on engineers and technicians, giving them a framework to use their engineering education to come up with mitigations that serve the needs of the process. CIE hopes to take advantage of the existing industry safety culture and many of the actions that are performed as a part of that culture to advance the culture of security and align the cybersecurity mitigations that are put in the digital technology frame with the safety mitigations that are put in the physical technology frame, so that all of them prevent the potential for an adversary to have an adverse effect. As a part of cyber-informed engineering, the Department of Energy was directed by Congress in the year 2020 to create a national cyber-informed engineering strategy. In that, they outlined the core concepts of what is this? This is kind of crazy. We're going to have engineers doing cybersecurity, but they're not really doing cybersecurity. They're doing engineering. So we really needed to explain that idea and put some examples in place so that there would be some good thinking about how to do this. In the strategy as well, it was recommended that we offer cyber-informed engineering across 5 different pillars: making people aware of this, including it in education, building a body of knowledge, and that's where our focus this afternoon is going to be, applying it in the existing infrastructure that already needs protection, and then determining how we could incorporate cyber-informed engineering in the next generation of technology that may just be at the research phase. Even if I'm making a Diet Coke and Mentos reactor and I'm just drawing it on the piece of paper and I'm at the original technology phase, I could begin thinking about how to engineer cyber resilience into my experimental design and ultimately my pilot. The strategy was issued in 2022 and is available if you'd like to read that. Also in that strategy, we defined 12 cyber-informed engineering principles, and we are going to go into each of these in depth this afternoon and explore each one. They each offer a slightly different perspective of how engineers can think about digital technologies used for engineering applications, but you do not have to do all of them to begin thinking about cyber-informed engineering. This is simply a framework to give you all the different perspectives you can consider. We're going to start with a real example this afternoon. Rather than just talking about it, I'd love to invite you to join me as we work through cyber-informed engineering together. Before we go into that, one of the wonderful things about standards, and we've talked about several in the last 2 days, is that there are so many of them. There are so many ways to talk about how we might protect our systems and networks. And our intention is not that cyber-informed engineering becomes YAS, yet another standard, but instead that the standards that we already have begin to incorporate how did we think about engineering and physical properties to shore up and make deep our cyber defenses. So whether you're doing 62443, which we've talked about, cybersecurity framework, we haven't talked about bow tie analysis, but this is very popular in oil and natural gas and is a great way to visualize what risks you might face and how you prevent and recover from them, or any of these other hazard analysis methodologies. If you train your hazard thinkers and your safety thinkers to consider cyber, and your cyber teams to reach out to engineers and ask the questions that we'll talk about this afternoon, that is how you can do cyber-informed engineering without requiring yet another standard. So I'd like to move to practice. That was one of the benefits of this conference, is that we paired research and practice and spent a lot of time getting our hands dirty. So I'd like today's workshop to be no exception to that. And because we've talked about the water sector this week, our example is going to focus on the water sector. So I would invite you, wherever you are, whatever you're doing, leave your job, leave your career, come and work with me at the municipal water company, and we're going to work together to put some cyber-informed engineering into an application that they have. Our municipal water company, thank you all for accepting my request and coming to work with me, we operate a municipal water system for a number of residents. In order to keep the pressure in that water system flowing, we have what are called water booster pump stations. And these are dotted around the city, and they ensure that the pressure in our pipes for any subscriber are consistent with their needs. So that if you're operating a car wash, you don't get a dribble of water while the household nearby gets a spray. The water booster pump stations keep that pressure consistent, and they help to ensure and discourage they help to ensure the safety of our water by discouraging the growth of biological agents. Each water booster pump station is also a place where we can check in on how the water is going through the pipes, what is the health quantity of that water. If we need to add more chemicals, we can do that from a regional perspective instead of needing all of it to go from the central office down to every drop of water. So these water booster pump stations are very important localized aspects of our water service. And as you heard Charlie talk about earlier this week, the water company that we work for, we don't just deliver water, we deliver trust. Every member of our city experiences our water system as something that they can completely rely on, utterly forget about, depend on, and know that it will be there for them always. And that's part of our job. However, it's very expensive to maintain these water booster pump stations. What we do right now is send 2 people in a truck to visit each one and do maintenance throughout the season. Several times a month, 2 engineers will come into a water booster pump station, calibrate the pump, evaluate the pressure tank, check all the pressure gauges, take a look at water quality, and potentially add chemicals to the water. This is something that's expensive. We'd love to do all of this work from the central office instead of sending all these engineers out. So you'll be delighted to hear that we got a grant. We're going to buy cloud-based monitoring and control to add to our system. Each water booster pump station will be connected to this cloud-based system. And from the comfort of our central office and our air conditioning, we will be able to start and stop the pump. And we have an idea for other requirements that we're thinking about with that system. You're going to advise us on some of those. And that will create efficiencies in how we operate, because our engineers will be available for the needs of the system, the needs of the day, rather than being on these constant trips to the various pump stations. So we're very, very excited about this grant. The first thing that we did was the smart thing. We took a look at the cyber maturity of both the system and the providers. When we looked at the control system software, they use a secure development lifecycle. They demonstrated a software build in front of us and showed us exactly how they track bugs and issues and how they keep their code up to date. They provided us a software bill of materials we didn't even have to ask. And when we checked out that software bill of materials, the component infrastructure was completely up to date. There wasn't any 5-year-old component with level 10 vulnerabilities. It was all looking fairly good. They also told us that they would release updates to the software on a monthly basis, and that they would work with the cloud provider that we had chosen so that we had notification of the software coming in, a chance to test it in a test instance, and that it moved into our operational location with the cloud provider without us having to do anything. They also have 24/7 support availability for either our questions or for incident reporting. So as you might imagine, we were pretty impressed. We also checked out the cloud provider and determined that they were reputable and qualified. They carried certifications for SOC Type 2 and FedRAMP, and although we don't need all of that, that was a great indicator of their maturity. They also had great physical security, and they showed us the gates and the guards and the guns and how they respond physically when there is a safety or security incident. We ensured that they had experience hosting solutions like ours, that they didn't just do financial and data stuff in their cloud provider, but that they understood what it meant to support critical infrastructure. And indeed, they took us through their client list where they host a number of water services, much like the one we're buying, included other customers of our software provider. They also demonstrated how they could move our solution from one container to another and how we would not see even a glimmer of interruption in our operational capabilities when they did that. Our team walked away very impressed, feeling as if these providers were the right mature solution providers for our need. We then looked internally, because buying a new solution and not having the internal capability to use it and protect it and not having it integrate with the tools linked to our security would be a failure. So we took a look at our own tool set. We determined that we could inject this into our network using our standard security package. We did not have to buy any new tools to connect up to the cloud, and the logging and monitoring off of that interface could go into our enterprise management system, so that just like all the other logs and all the other indications that we get, we would get indications from this service if there was any discrepancy, if we want to look at the traffic that's flowing through it. All of that we could do right from our enterprise management system. Our SOC could see it easily. We also determined that the traffic in and out of the system was encrypted between the cloud provider and our internal network boundary. And that gave us some surety that someone out on the internet was going to have a difficult time breaking into that traffic stream and getting into our system. So with all of that information, we called together an organizational review board to take a final vote about whether we want to move forward with this project. Finance and accounting gave us 2 thumbs up because it's going to make things cheaper and better, and they always want to move us forward into the future. IT was delighted that this solution leveraged the tool set that they were already familiar with and strong in using, and they voted to go forward. Cybersecurity was very impressed with the capabilities of the tool and the security of the cloud provider combined, and how that was going to work effectively for us. Engineering operations, however, was kind of quiet at this meeting, and their sense was this was a really, really big step for our small water utility to take. And although they love the mayor, they want to make sure that we don't meet the mayor because of some cyber attack on the water system. They wanted to make sure that this system would be an augment to our operational capabilities and not something that we regret. So they asked for permission to do a little more thinking and apply cyber-informed engineering to see if they could deepen the protections that are on the system. And you, my friends, are going to help them. I'll refer back to the diagram that we have here when I need to explain certain things. But again, I wanted to show you a picture of the system that we are working on. We have our water booster pump station. We have a pump that we can turn on and off and slightly calibrate. We have a pressure tank, and I'll talk a little bit about the function of that pressure tank. And we also have a chemical feed and water quality monitor. Currently, those are analog, but there's the potential to digitize them as part of this grant. We're going to work through each of the 12 cyber-informed engineering principles and using this example and explore how the insert of this new cloud-based monitoring and control can be effectively defended by using engineered controls and aligning them with cybersecurity controls. The first principle that we start with in cyber-informed engineering is consequence-focused design. In this principle, we ask, how do I understand what critical functions my system must ensure 24 hours a day, 7 days a week, just like the water system, and the undesired consequences it must prevent? And we heard some of those from Charlie this week. We don't want to get people sick. We want to make sure that their water flows when they need it, and it doesn't overflow to a point where it causes damage to the water system or their own homes or businesses. So as we think about consequence-focused design with this new cloud-based monitoring and control system, we have to think about what's the worst that can happen. And if you are still awake and excited on this Thursday afternoon, or at least as excited as I am, I'd love it if you use the chat to think about what's the worst that could happen if an adversary got ownership into this cloud-based monitoring and control system. What are the worst things they could do? Then we have to think about how would we respond to what that adversary could do, and would any of these issues be catastrophic? So Jeremy and I will discuss a few with you since I don't see any entries in the chat yet. Jeremy, what do you think the worst thing is that can happen? First of all, what about our data? What could somebody do to our data?
Well, from a data perspective, there's a couple of things that I think would be concerning. The first is if you compromise the system all the way down, you can actually learn about how is the system architected based on the information flows and what's flowing back and forth. And I'm getting a little ahead of myself, I think, because this does get into one of our principles a little further down the road. But one of the things I think that we need to think about is, and we touched on this a little bit, right? The information security side of things doesn't completely go away in cyber-informed engineering. It's still a consideration. And while we are implementing engineering-based controls to try to mitigate the kinds of cybersecurity issues that might arise, that doesn't mean that you can't completely ignore cybersecurity. So from a data perspective, right, you really want to understand what are your data flows, what is the information that's contained in those, and how can that data be manipulated to do things?
Okay, so it definitely sounds like they could understand the seasonality of our water system, when we turn the pumps on, when we turn the pumps off, how often our folks operate this system, and understand our usage patterns. I see in the chat that they could remove chlorine addition, leading to possible health issues to consumers. And Matt, that's a great concern because that potentially could be catastrophic. And as we think about the requirements of this cloud-based system, we may want to think about whether interactions with the chlorination system should be in our phase 1 set of requirements, or whether we might want to get used to the system first and have that be phase 2. That's a great suggestion. And yes, that could be catastrophic. Another thing that could happen is an adversary could conceivably come through the system. Okay, Andrew, you went right to the chase. They could turn the pumps on and off. And if I could turn it on or off, then I can turn it on and off, and potentially so fast that we risk either tearing the pump apart because of the rapid change in torque, or one other challenge for this pump is each time I turn this pump on, the electrics fire up and heat is generated. And although there's insulation in the pump to dissipate that heat over time, if I turn the pump on and off and on and off and on and off and allow the electrical inrush to happen and the heat to build up over and over and over for minutes at a time, that insulation actually degrades. And so not only could I tear the pump apart by torque forces, I could burn up the insulation and overheat the parts that are in the pump. Now, if my pump breaks, I could go and look at it and I could see the magic smoke coming out of the pump, but I may not be able to get a crew to work on that pump and fix it, particularly in Andrew's example, if it's broken. So would that be catastrophic? Well, we called up procurement and we did a little bit of engineering analysis. And to get a replacement pump for our water booster pump stations, because they're not very modern and these things aren't on deck at Walmart, it's going to take us about 18 months. So we have to buy the pump, we have to do a competition, we have to get special funding permission. All of this is public process. We've got to then install it once the bidding is done. And then we have to have the EPA come out and recertify our installation. Head to tail, that's an 18-month process. And although we could leverage other water booster pump stations in the system for a while, that's a pretty catastrophic outcome for us to be recalibrating the system for an 18-month outage. In addition, one of the engineers noted that he's not a cyber expert, but it seems like if you could do this to one water booster pump station, turn them on and off really fast and break the pumps, you could probably do it to all of them. And if all of them had a pump that was broken with an 18-month outage, we are now into importing water from an external entity, having trucks with water bottles and boil water orders, and that is not a place our water company wants to go. So that is a potential catastrophic consequence of a cyber attack. The only thing the cyber person is doing is turning the pump on and off, but for us, it could have ramifications lasting several years. So we've played with some ideas. Can the attacker adjust chemicals? And we've said, probably, if we put that in scope, that might be something they can do. Could they cause an outage? Well, they could turn pumps on or off, and that would be problematic either way. Could they break equipment? And looking at Andrew's example, they could absolutely break a pipe or break a pump. The good news is the pressure tank that we have, the way that it is formed, it has actually a large, think of it like a balloon, it's a bladder inside, so that if there is a water inrush, a water pressure inrush in the system, that pressure tank actually serves to absorb some of that pressure and mitigate it. So the good news is if an adversary does turn the pumps on and off and on and off and on and off, although they might cause our pump to be torn apart or they might cause it to overheat, there is an effect called a water hammer effect that you can have if you build up pressure in a pipe and give it limited avenues to travel. That, at least our water pressure tank can save us from for most things that we think this pump is capable of doing. So the good news is we have a cyber-informed engineering solution in place, at least for damage to piping. Okay. So we've identified that an adversary turning pumps on and off rapidly is something that we might have a lot of digital defenses against, but once an adversary gets the ability to do it, if they somehow broke into the cloud provider and had the ability to send that traffic, we might want some additional controls to prevent that from being catastrophic. If it were to happen right now, the way our system is configured, it could potentially be bad. So if we put this as what we're thinking about, our scenario is attacker defeats security, turns pump on and off quickly to damage equipment, resulting in an 18-month outage, large repair, and replacement project. We'd like to think about an engineered control that would make that attack less impactful. How could we do that? Jeremy, do you have any ideas?
Well, we want something deterministic, governed by physics, not networked.
I see a suggestion from Matthew. Use a motor overload relay with a manual reset or a proper breaker with a thermal trip.
That's a good solution.
Matthew, are you an engineer?
That does have one drawback though, right? A manual reset does mean that you have to send somebody out to the station to reset it if you trip that breaker or if you trip that relay. So there might be something related to that that's close.
Okay, and just as insight on that, we did some analysis, and if we put 2 folks in a truck, we could get to any of our water booster pump stations within 2 hours. So the analysis indicates for 1 water booster pump station, we could probably remediate even a trip if we had to without it being significant. But if the attacker was able to do this and cause a trip at multiple of the water booster pump stations, we start risking damage as we get into 2 hours here, 2 hours there, 2 hours there.
And Andrew, again, I think hit the target idea, which is a timer relay. So a timer circuit to delay the restart after a shutdown long enough to cool off the complementary start is kind of the right thing. These are small relays with a settable timer. When the pump turns off or turns on, that timer runs and you can't switch modes until that timer expires, allowing you to then go from on to off or from off to on after that timer expires.
Okay, so that control is deterministic. It's governed by physics. We know what it's going to do. It is not networked or digital. And we did check with the engineers. We can install a time delay relay if that's what we choose to put in on a normal outage. So it would take us a little bit of time to go through all of the water booster pump stations, but we don't have to call in external support to do it. Accounting and finance is always curious about how much this stuff is going to cost. And we did learn that a time delay relay costs about $20. So that seems to be a cyber defense mechanism that is well within our budget, even if we put it in 25 water booster pump stations. And it's complementary with our existing protections. If we do have a time delay relay where, and in this case, what we're suggesting is if you operate the way that a time delay relay works is when I send a command, it starts a clock. And if you imagine a kitchen timer, that's kind of how this device works and sort of what it looks like. And it will tick down, and I can't execute another command until the time is up. So imagine ding, and then it will take another command. I can set a time delay relay for any time period that makes sense. Often they're set to be just a couple of minutes to allow for thermal disbursement so that we don't build up heat. And they're not unusual to have in industrial environments because if you flip the buttons too fast, you can really damage equipment, even if there's no cyber impact. So these solutions are available. They're well understood by engineers. And in this case, if we had a time delay relay in place, an adversary wants to turn things on and off and on and off and on and off, and our time delay relay would allow them to issue one of those commands, maybe an on or maybe an off, and then hold for, let's say, 5 minutes. That would be enough to allow that thermal inject to disperse enough within our installation's capabilities, and then they could send the next command. We anticipate that within 2 hours, we could send somebody to 1 water booster pump station, and within around a day, we could service most of our network. So that is how that time delay relay would work. Each of the solutions that have been suggested have the potential to be effective engineered controls. As you're looking at these, each of these limits what an adversary is capable of doing while allowing the system to operate, which is important to us as a water system. Okay, those are good examples of engineered controls. Often when we think about engineered controls, we can use the hierarchy of controls from safety to identify ones that might be good, better, or best. And the hierarchy of safety is used for safety applications. And of course, the first thing we want to think about with safety is, how do I get rid of a hazard? The first answer, although not practical in some situations, is, well, what if you could physically remove the hazard? What if you could take that hazardous thing out of the way and you could continue to do your work without that hazard pressing you? Well, as we apply it to cybersecurity, elimination means, is there some way that I could completely eliminate this avenue for attack? One choice would be, don't go to the cloud. I would completely eliminate this avenue for attack. But we've said we want the cloud for a number of reasons. So we have to evaluate, is there any way that we could eliminate this risk? And if we can't, we keep going, pushing through this pyramid. The second answer is, can we somehow replace this hazard with something that is less dangerous? And I told you earlier that I would talk about our incident response training out in the desert with radiologic materials. It would be very exciting indeed if we put real radiologic sources in the Idaho desert and incident responders maybe didn't find them all, so that we had radiologic material going through it and potentially impacting animals or people or plants. And so we don't do that. We have to have these people trained. Their training requires that they use the tools that detect radiation because they have to train in a realistic environment. So we use a simulant that their radiation detector will detect. And sometimes an example of a simulant, bananas, they set off radiologic detectors because of the potassium. Certain kinds of salt will set off a radiologic Geiger counter or other detectors. And so we can use a substitution, put those sources out into the desert, allow the people being trained to detect them and train against them, and know that it is not dangerous. And if they don't recover all of them, or if they make mistakes during their recovery process, we've substituted the actual hazard and let them do the training. In cybersecurity, substitution might be some way of maybe not going through a cloud provider, but going through a private network that is more closely controlled. That might be a difficult thing for us to think about. So in this case, again, we're going to push through substitution and go to the next level of the hierarchy of controls. That gets us to engineered controls. And if you've gone up a set of stairs today, you have probably used an engineered control. That banister on that set of stairs, if I am on the stairs, the worst hazard that everyone worries about is, of course, that I fall off the stairs. The banister is there as a physical device that isolates me, my body, from the hazard of falling off the stairs. It's there to physically prevent me from doing the dangerous thing. So an engineered control, the challenge with an engineered control is that they can break, or that they may require their own maintenance. Sometimes they can be expensive, but they do allow me to isolate from the hazard. In our cybersecurity idea, the time delay relay serves as an engineered control. It is a device, it's electromechanical. It isolates the adversary from the ability to do harm by taking their ability to effect a command away for 5 minutes or 30 minutes or whatever our setting is. It isolates them. It doesn't eliminate the hazard, but it does make it so that it doesn't cause us any harm. To keep following the hierarchy of controls, we can use administrative controls. These are rules, regulations, password strength. Everybody loves putting 2 special characters, a number, a capital letter, and all of that in their password. That's a great example of an administrative control. It does make the difficulty level for the adversary worse, but sometimes people forget to do it, or some systems don't get addressed. So administrative controls do have a higher propensity to fail. They are, however, cheap to implement, and that's a huge benefit of administrative controls, and one of the reasons that often we go here first. The last form of protection that we talk about in the hierarchy of controls is personal protective equipment. And if I was in a safety situation, let's say my job was cutting things up with a knife, personal protective equipment might be cut-resistant gloves. These are chainmail gloves, and yes, you can order these on Amazon. So that if you are cutting up bagels or whatever your morning thing is, if you're wearing these gloves, the knife will go through the bagel, but will not go through your hands. The challenge with personal protective equipment is, unlike an engineered control, that worker is interacting with that hazard up close and personal. If there's a chink in that chainmail on the gloves, that knife could impact the worker and cause a hazard. An idea or an example of personal protective equipment for a cyber issue is, what if I have monitoring on the device? What instead of doing something that's physical, I'm going to have some sort of antivirus or some sort of monitoring that's going to try to detect these commands and not allow those bits to go through. Much like personal protective equipment, I am protecting the device from the adversary, but I am taking the risk that the protection is very close to the device and it's right in frame with the event. So if anything goes wrong or the adversary gets past my protection in a novel way, their ability to execute the command is the next step. We use the hierarchy of controls for thinking about different kinds of engineering controls and trying to prioritize them. Again, often the most effective may be the most expensive or the hardest to implement. Some of these methods of controls may not be available in all environments. So often engineered controls is a place where we have a lot more flexibility to surround our system and think about what happens. And that's why this principle is named after that particular step in our pyramid. Anything else, Jeremy, on engineered controls?
Couple things. One, I like to talk about one of my favorite examples of isolation. It's one that we see every day, and it's the dot bar on the back of semi-truck trailers. So some number of years ago, a famous actress, and it escapes me who that is, ran into the back of a semi-truck, and her car went under the truck, and she ended up dying. And so dot bar, this big heavy steel bar that now hangs off the back of every single truck, is another example of, ways to isolate from the hazard. It doesn't completely eliminate it, right? Because we still have semi-trucks on the roads these days. But that bar does keep cars from going underneath the trailers if the car hits the rear end of the trailer. One other thing about PPE. We have a lab manager, or lab managers here at INL are the folks that are fairly high up in our safety hierarchy. He likes to say that if our only control is PPE, we probably need to step back and rethink what we're doing, because PPE should not be the only solution. Sometimes it is, but if we can find something further up this pyramid to help us, instead of just PPE, we're probably thinking about the problem in a better way than, just put on a pair of gloves.
Okay, thank you, Jeremy. So in this case, and I have a picture of a time delay relay here, we have, again, a electromechanical device. It's not networked. I can't I can't talk to it via wireless. I set it with these dip or dim switches. I never remember which those are. And that's the timing that it will operate on. The downside is I do have to do some maintenance activities and make sure that it still functions. The good news is it's not very expensive. This controls the temperature and the wear and tear on the pump so that even if an adversary tries to launch this attack, this time delay relay will make sure that that attack can't land. This fulfills our description of an idealish control. It's not very expensive. We can install it ourselves. Again, it's not networkable. We understand how it works. I've got a note on the slides that we could have thought about manually governing pumps settings. So control the kind of calibration that the pump can perform. And we'll talk about that a little bit later in our conversation. I'd like to move on to our next principle. And this one is kind of the hardest for engineers and IT professionals to talk about. It's innocuously called a secure information architecture. And if you are a traditional cybersecurity expert, you're going to go, oh, I totally have this. 62443 would say this is zones and conduits, and it's how I segment my information and make sure that I'm keeping important data on a different network connection, and I just don't have everything going through the same pipes. And we'll get there. But when I put my engineer hat on, secure information architecture really takes a different tone, because my engineer probably doesn't understand or want to get involved in the network architecture, but they have some very special knowledge that's important for us. They understand what data is going through this system that's actually important for our consequences. So what of the data fields in this particular system would really matter if an adversary got hold of those? We talked about an example at the very beginning of this conversation about pipe diameter. And in that case, the engineer might say, oh, you know what? The volume of chlorine, that's not really an important piece of data to worry about from the attacker's perspective, because we've got that pipe diameter and that controls what actually goes through the pipe. So I don't care if the attacker sets that thing to 5 million, the pipe's going to govern what flows through. There may be other data elements of the system, in this case, like the on-off switch for the pump or setting for the pump, that the engineer says, oh, now that I think about it, that is a very important piece of data, because that data leads directly to one of our catastrophic consequences. An adversary that has access to the on-off, on-off, on-off has access to the health of our system. The way that we use this kind of thinking is to inform where in the system do we need to apply protections, what elements of data need the most protection from manipulation. And in some cases, that will prioritize how we leverage cybersecurity defenses. That might inform the zones and conduits conversation that happens later on. It also might inform where I put engineered controls. In either case, it is likely not something that the IT or cybersecurity protection team for this system understands without the engineer's help. Anything else here, Jeremy?
No, I don't think so.
Okay. So in our system, we ask the question, where could manipulation of data lead to engineering or operational impacts? And we could look at the flow and pressure transducer, because that could lead us, if we could really muck up the flow, we could lead to a problem. But again, here, our pipe diameter will control what is possible. We have already talked about an adjustment to the chemicals could cause an impact on safety. And we care a great deal about safety. So right now we're considering putting off the chlorinator until phase 2 of the system. Let's get good at the system. Let's understand how it works. And then we'll think about adding adjustment to chemicals. And we've talked about some ways that we could make sure that we can do that safely, even if an adversary has access to our digital system. We have operational impacts in loss of productivity and revenue if an adversary turns off our pumps or changes the pump settings so that they flow with water trickling or spraying in ways we don't like. And finally, we identified that we would have damage to property if there was an on-off switch with that pump cycling. And if we got the pump to overpressure, to fly apart because of a torque issue, or to overheat. In our system, these data elements, the data in the flow and pressure transducer, the minute amount of chemicals, the on and off of our pumps, those were the critical data elements that we identified as the information that we need to build security around. The rest of our thinking is going to look at those data elements and add engineered controls. So we've talked about one already that allows the pump cycling to happen based on adversary action, but limits how often it happens. As we do more analysis, we'll look more closely at these other data items and see what we can do to protect against them. In some cases, the best way to protect data may be leveraging digital systems, potentially with some analog monitoring to add on, but we'll evaluate that as we go. The important thing in secure information architecture is that we identify what are those data values that we really care about so that when people come to do zones and conduits, we can have an informed conversation. Our next principle is design simplification. In design simplification, we determine what features of our system are not absolutely necessary and how we could eliminate them. Here we're back on that hierarchy of protection slide, and we're thinking about how can we get rid of a feature that could serve as an attack vector for us. And in many cases, we can't eliminate features. Anybody who has a cell phone is carrying around a whole pocket full of features that they may never use, but are intrinsic to the phone. We can configure them out, and that means we can't use them, but it does not mean that an adversary can't reactivate them or use them in ways that we didn't expect, just like we talked about in the Trisis Triconics issue. So we're going to explore some design simplification with this water booster pump station. When we built the pump station, we thought about operating this pump via a network connected variable frequency drive. It was all the rage at that time. It was fairly novel technology. And we thought, that will mean that we can calibrate these pumps to be very efficient on our water system and our power, and we can operate them only to what we need. And that would be a huge benefit. When our engineers talked about that, they thought about, is there a simpler way to do it? Do we need network connectivity at every water booster pump station? Are we going to want a controller that has this many settings and this much complexity for our system, or is there equal benefit in doing something simpler? So in this situation, they elected to go with a relay-driven pump, and the one engineer that was excited about variable frequency drives was really disappointed. But the nice thing about the relay-driven pump was that it was electromechanical and simple to operate. It was probably cheaper as well. It didn't allow us to accomplish some of our power and water efficiency goals, but it meant that we just had a lot less to worry about with the system because there were less settings and it was much easier to calibrate. This is a great example of design simplification. We took a capability that would have been very complex to configure and maintain and replaced it with something that was much simpler and far less digitally connected. Again, in many cases, systems you buy, large software systems, cell phones, whatever, you may not have this amount of flexibility, but it makes sense to look for it. In the case where you have a capability that you can only configure out but can't eliminate, we recommend thinking about how you will monitor for its use. If you have configured it out, you've trained your brain to think that that capability is never going to be in use. And that means you're likely not looking for it, and you might not even see it as a threat. And so when you configure something out in a digital system, if you can also set warnings or even limits on your network, so that if the traffic was flowing, you get an alarm, or the traffic is not conveyed to the ultimate system, doing those things in parallel, although it's not a design simplification, it at least ensures that configuring a feature out has more effect than just making it inaccessible to you. Jeremy, anything else on design simplification?
Yeah, I think the hardest part of design simplification, or at least for me, it really is that last thing you were touching on, right? You can't just think about what is the system designed to do and how do we simplify that, but what are the things that the system can do that maybe we're not thinking about, that you've got a relay, a VFD, right? A variable frequency drive that can, do things beyond just start the pump and stop the pump. Even if you have it configured so that your pump speed is preset within the VFD, that doesn't mean that somebody can't come along and work around those configuration parameters to make it do something maybe you're not thinking about, right? And so taking that step further to, now we just have a switch. It can only be on or off, right? You've completely eliminated those sort of intermediate capabilities that maybe you're not thinking about. And understanding where those things still exist, and as Ginter said, right, monitoring for those where you can, even though they're configured or you think that capability is disabled. And sometimes this means, having conversations with manufacturers, right, because the manufacturer may be building in capabilities that they're not even telling you about because they use the same controller chip for their entire line of products. But an example, right? BMW. BMW now charges a subscription for certain features in some of their cars. It doesn't mean that the feature isn't there. It just means that it's disabled or turned off. And understanding that the capability is still there, even though it's disabled, and how to monitor for its use and so on and so forth is really, really important around design simplification.
Thank you. Okay. So one of the things that we also decided to do for design simplification is we decided to manually limit the range of pump settings so that when beyond on and off, we can set the pressure on the pump. We decided that for every water booster pump station, we would manually govern that pump to only operate within a set amount of pressures appropriate for normal operational use. If we need the pump to operate outside those guidelines, we will go in person, remove the governing, and operate it manually after taking our cloud-based system offline. This is a great design simplification. We made it more complicated for us, but the features available to an adversary are less than originally available. They did have a wide amount of pressure that they could set the pump to. Now we've calibrated it to just the ones that are appropriate to our use. The next element of cyber-informed engineering is layered defenses. And this is where we begin to bring in, we've been talking about mostly engineering from here or from the beginning to here. Layered defenses is when we start to join with our cybersecurity counterparts and think about how many defenses we can put, especially towards those most catastrophic outcomes. With traditional cybersecurity, we would secure like the whole system. With layered defenses, we want the cybersecurity team to be aware of those consequences that would be most catastrophic for our system and prioritize those protections in ways that are appropriate to those systems and those consequences. In this case, with layered defenses, if we identified that an adversary turning on and off the pumps was the worst potential engineering consequence, we ask, how can cybersecurity prioritize the defenses from our side and from the vendors to detect or prevent that from happening? Engineering has the time delay relay, but we'd like to make it a whole lot harder for the adversary to do this work. And if we could detect it at the cloud provider before it ever gets on our network, that's a potential win. How many layers of protection can we assemble for our most catastrophic consequences? Again, this is a thing that could take us offline for 18 months. If this ever happened, we would meet the mayor in the worst way. And so this is one where we may want to work with cyber to pull out even the things they don't normally do for this particular consequence. And then based on this, how do we inform the cybersecurity requirements that are developed for the system? Some of the things that we thought about for this system were limiting the allowed behavior on connection to the software. How many commands could go through? What is the data throughput? Are there limits on what IP addresses can initiate traffic or commands? Can cybersecurity help us with those kinds of things? Should we have people check the logs, maybe weekly, monthly? Certainly we could add encryption. Are there other defenses that with our time delay relay, we might want to have? Bandwidth shaping, you name it. And although our engineers aren't the ones that will implement those technologies, this principle allows them to give the requirements to cybersecurity teams and cybersecurity teams to really think about what capabilities might best answer the needs.
So this is,
oh, go ahead.
Yep. So this is really in again, Ginter, already mentioned this. This is where your traditional cybersecurity really comes into direct contact with the engineering side of things, right? This is where you can take advantage of those relationships, have those conversations, help your traditional cybersecurity guys understand the engineering side of this and what those consequences really look like, and where your traditional cybersecurity folks can help the engineering folks think about things that maybe they don't think about, like information flow back and forth, and what kind of information, right, to ask those questions. What kind of information is going to be contained? What do we care about, right? Do we care that the on-off status of our pump is flowing out onto the internet, even if it's encrypted, flowing out onto the internet for the world to see? Does that matter? Or do we have a greater concern about the control packets coming from our cloud-based SCADA system going down into the pump controller, turning our pump on and off? And those conversations, you can really build really great relationships based around these kinds of conversations that get into, again, kind of getting ahead of myself a little bit, right? Building around that cultural change to really organizationally, as a whole organization, think about what cybersecurity means, what it means from an engineering perspective, what it means from a traditional cybersecurity perspective.
Okay, our next principle is active defense. The question that we ask in active defense is, how do I proactively prepare to defend my system from any threat? And by proactive and cyber-informed engineering, we mean really proactive. While I am designing my system, If I can take it as an assured truth that I will someday face a cyber attack, I might want to, even at design time, start thinking about what that defense will require, whether it is personnel or it is policies and procedures, or it is these engineered controls. In some cases, I don't have to write the details of each one of those during design time, but it's helpful to at least open that box of consideration. So if we identify that an adversary turning on and off pumps leads to our worst engineering consequences, first, how would we defend against that action? What tools and capabilities do we have? What do we expect of our vendor if that takes place? And do we need additional contracts? Do we have the resources that we need? How will engineering and cyber work together during the defense? Or will engineering see something happening and cybersecurity also see something happening, but no one connect the dots? And then most importantly, we talked about exercises a little bit. Have we documented and practiced the defense that we plan to make sure that it's possible and to make sure that it is part of what our team can readily do? So let's walk these down. How would we defend against that action? Well, the time delay relay gives us some protection. We have manual pump limits, and we can drive to the pump stations and take the cloud system offline and operate them manually. We won't want to do that, but we can. It's a possibility for us if things get really, really hairy. After all, we're doing that now. What do we expect of our vendor? Well, we'd like them to alert us when they put a patch in. We'd like to know if there are vulnerabilities in the system that an adversary might take advantage of. We could have them do some traffic monitoring on our connection and make sure that the traffic that's flowing to and from is only us. Because if they see a host that's not supposed to be there in the communication, they could tell us something was happening, and that might help us with our defense. We would also like the ability to drop and restore the software container that we're in and move to a new environment with a new IP address and new networking in the case that something happened. How would engineering and cyber work together during defense? Cyber monitors the traffic. Operations advises whether we can close the service connection and take things offline. Operations performs manual operations, restores functions, and does remediation if necessary. Cyber may come in and restore any of the servers or the infrastructure associated with the system and make sure that we don't still have adversary connections to them. The cyber team also works with the vendor and the provider on the response. They restore local systems, they restore the connection when ready, and they monitor the digital part of our recovery. Documenting and practicing our defenses, well, we've decided that we now need at least a yearly exercise with our cloud provider and our software provider. And that we'd at least like to every month open up the incident response plan and read through it, maybe drinking a cup of coffee, but identify those critical assumptions that are part of that plan and make sure that we still have the personnel and the skills. Is the key still in the top left drawer of the gray metal desk where, the incident response plan says I should look for it? Is it still in an Altoids container? Whatever the assumptions are that are in that document, at least monthly, we want to test those out. Jeremy?
So this is one that always makes me smile. Ginter and I have a mutual colleague from the New York area who we were actually doing an exercise, and his response. Now he's an electric power. He was. Unfortunately, he is no longer with us, but was a system operator, and he was very quick to say, first thing we do, we're going to put it in manual, and we're going to run this thing by hand. And while that isn't a complete solution for various reasons, right? We talked about response times and so on and so forth. forth like that. In this particular case, right, that first step, understanding, what are we going to do? How are we going to, what is the first thing we're going to do to defend the system when the system is under attack, right? They had an organizational culture that was so well built in that they knew what those steps were. And so, and for this particular principal always makes me think of him and the fond memories we had working with him.
I do miss Dan the Man. It was a great, again, one of the best things we get out of cyber-informed engineering is that understanding of what's going through the engineer's mind in this circumstance and what's really happening at a digital level. And in this case, Dan didn't understand that the adversary had already been in, and that when he switched it to manual mode, essentially he was locking himself in with the adversary. The central office couldn't help him anymore, but the adversary got there and put all their tools on the systems way before he ever was there to put it in manual mode. So it's important in active defense to think about how that defense is going to work, what your adversary is doing. As Andrew Ginter said, look at some attacks that may have happened in your sector and make sure that your defenses can live up to those. Okay, we've gone a significant way through cyber-informed engineering, but we have a significant amount left to go. I would love to take a quick break. And if we can have folks meet back at 3 p.m., we will go through the last of the material.
Thank you,
Prakash, is that
Ginger and
okay with you?
Jeremy. Yeah, I think you guys have been awesome. I think I want to give a break for you guys. I think, yeah, let's take a 10-minute break, or maybe we'll be back at 3 p.m. Central, so stay tuned.
Hello, everyone. It is now 3 o'clock Central Time, and we're going to start back up again.
Can I just say something?
I would welcome.
Yeah, for those who are needing certificate of participation or certificate of award, or with the PDH, I think you need to take an assessment. We will send instructions to you after the workshop. Sometime tomorrow, we'll send you the instructions, so stay tuned for that. Thank you, Ginger.
Thank you, Prakash. We are continuing in our exploration of cyber-informed engineering with the next principle, and that is interdependency evaluation. And when we think about interdependency evaluation, the question that we ask is, how do I understand where my system can impact others or be impacted by others? Before we dive into our system, I would remind you of the Colonial Pipeline incident that we talked about, where ransomware to IT systems resulted in an impact on production and operation for the entire Colonial Pipeline. In this case, Colonial neglected to understand an operational interdependency that they had for that manifest file that we talked about, and to understand its impact on production. Could they have developed some manual workaround? Could they have had backups or spares? We don't know, because those weren't decisions that they made. But when we perform interdependency evaluation, that kind of a show-stopping interdependency where another system or some input or output could lead to one of our catastrophic consequences is exactly the kind of thing that we are trying to uncover. In this case, for our water booster pump station, we have added a new interdependency, the cloud service and the software. Beyond a specific cyber attack, how might that interdependency and any instability in the service affect our operations? Essentially, what happens to us if this service goes down? As we start to think about that, our software provider could provide us with a bad patch, maybe like a CloudStrike incident. We don't want that. There could be unexpected functionality. Jeremy mentioned that earlier. They could put in a feature that's not something that we use. I talked to a vendor who was trying to put in a feature that would have a secondary approval required for critical operations. And while in some places that could be great, that could also be a feature that doesn't align at all with how the implementing asset owner works. There could be maintenance or other connections to our system that we would want to know about and control. We now have a supply chain. How are patches provided? Are they developed by the software company and only the software company? Is there open source in that? How does it get to the cloud provider? So many questions that we have to think about. How is the software kept up to date, especially the open source components within the tool? What if there is ransomware of the cloud provider, or sorry, of the software provider? How would that potentially affect us? What if they have a breach and our information gets out? And that could be our customer information. Well, everybody knows the water company's address, but if it was the configuration of our systems or maybe critical security information, that would be far more troubling. For the cloud provider, we have a question about what if their environment goes down? We are now one-to-one dependent upon them for cloud operations. Yes, we could repair it, we could operate manually, and we're going to fight to keep that capability. But right now, if their environment went down, it would cause us a lot of distress. What happens if they have a breach? How do we get the notification from the cloud provider? Who does that go through and to? What if the connection doesn't meet our requirements? It doesn't have the throughput we need. It doesn't provide us it has too much latency, or it's simply not the connection that we want. What if our software provider's software no longer works in their environment? The two part ways, and now one doesn't support the other. What if the cloud provider applies a patch poorly, changes our configuration in a way that we don't want, or there's a maintenance gap? What if the cloud provider's logs reflect undesired activity? Or indeed, what if we can't get logging information at all? We have to understand where a cyber attack on this cloud vendor could result in an operational attack on our systems. And that's what interdependency evaluation does. In this case, we could go through each one and how we might respond. And as we thought about interdependency evaluation, that's indeed what we would do. Jeremy, anything here?
One other thing to think about that I don't think we captured here. Do our vendors understand their own interdependencies? An interesting case example. I'm sure most of us have heard about the AWS outage from a few weeks ago. One of the interesting things that Amazon learned through that is that they have an extreme dependency on their US East 1 data center. In that problems at US East 1 can have very, very widespread impacts. And a simple misconfiguration of, say, a DNS service might take down what we know is half the internet these days. So, even not just your interdependencies, but your vendors, your partners' interdependencies can also have a big impact. The other thing is, Ginter mentioned it briefly, but I don't see it in any of our list here, but who has interdependencies on you, right? We're a water system provider. What happens if you do have a water outage? What are the impacts on your hospitals, your residents, so on and so forth? Those are also important considerations.
Thank you, Jeremy. And it's important to note that we think of Amazon as being extraordinarily mature, and even they misunderstand interdependencies. So that there's hope for the rest of us. Our next principle is digital asset awareness. This is another one where the cyber team thinks, oh, digital asset inventory. Yes, let's go figure out what all of our digital assets are. And we will get to that. But again, with the engineer's hat on, digital asset awareness actually starts far earlier in understanding what functions digital assets are capable of, then where and how they're used, and finally, what our assumptions are about how they work. That Triconics example where we had the key switch, and because you had a physical key, no one thought right behind it was software implementing the lock and unlock feature, is a great example of a lack of digital asset awareness. No engineer would have thought there was software behind there, and most cyber people would have assumed whatever that key was controlling was something electromechanical. And in this case, that was a critical assumption about how the device worked that kept the software or the hardware manufacturer from understanding a vulnerability. With digital asset awareness, we have to think about not what the device is supposed to do, but instead what it can do if an adversary pushes it and how that might impact our consequences. For our system, we talked to our vendor about extending the product to allow remote control of the chlorinator, even though Matt suggested we should not do that right now, and I think we agree. We're used to operating that chlorinator manually. How would the use of digital technology change the engineering risk in doing local chlorination? For that, we had some questions. Is the dispensed amount on the chlorinator when it's under control hardwired? In other words, it's always going to dump a half a cup or whatever amount of chlorine in the system? Or is it adjustable? Could I have an adversary dial up how much is dumped out or added to the system? And in this case, if it's dispensed digitally, how do we know that the product is actually dispensed? A fun attack might be giving us the logging and instrumentation to think that we're chlorinating, and meanwhile, the water is successively getting less and less safe. So in this case, the good news for us is there's a pipe that controls the total amount dispensed, and over dispensing would take a long time to make an impact. It's likely that we would discover it via other water monitoring before we got to an amount that would poison or negatively impact our customers. On the question of how do we know that the product was actually dispensed, we're going to have daily or weekly sampling. We do that anyway to detect anomalies. We have online chlorine monitors. They're digital, but we use them with our manual monitoring. And we have a non-digital sensor in the actual water booster pump station as well. So we think we can control some of the digital challenges for what an adversary can do. Anything here, Jeremy, before I move on?
No, I don't think so. Go ahead and move on.
Okay. Sorry, let me get my mouse in the right place. Our next principle is cybersecure supply chain controls. And this gets to something we've also discussed this week. We have done a lot of work to secure ourselves. How do we ensure that our providers are delivering the security that we need? If we use cyber-informed engineering, what can we do with our providers to strengthen their security? In this case, we looked at the components that the vendor and was using, and we looked at the security culture of the cloud company, and we were excited about both of them. However, we still have some questions that we need to ask. How is the system patched? How are patches delivered? Can I, as an asset owner, accept or reject a patch? And how does that process work? Is there something where I can reject any patch up to a certain amount of time, but then for every major version, I have to catch up with them? We're seeing that a lot in industrial systems. So I can delay a patch, but eventually I'm going to have to take that functionality. Does the software vendor or the cloud provider ever provide access to our system to their vendors and their maintainers? Is there some secondary support that might come into our systems, and potentially that might be a vantage point for a security breach on our part? How are third-party support providers, including the call-in support, qualified and vetted? All of those could be supply chain issues for us if we don't think about them. So again, we can do the analysis of these things and create a plan, but the important part is to have the engineers involved in that conversation and think about the catastrophic consequences that we discussed previously. Jeremy, anything on supply chain?
Yeah, another case study, I guess. One of the asset owners that we work with has a vendor who only does cumulative patches. And so this gets to what Ginger said about, maybe you can delay, but eventually you're going to have to apply it. With this particular vendor, they always build subsequent patches on previous patches, right? So you can't apply patch 5 unless you have actually applied 1, 2, and 3. Whether you need 1, 2, and 3 or not, or 1, 2, 3, and 4 or not, you still have to apply them in order to get patch 5. And maybe patch 5 is a vulnerability that you do want to address, or a feature that you need, or whatever. But it's important to be aware of that, right? That delaying is useful, but sometimes you will still be put in a position where you need to accept whatever risks are built into your supply chain, because that's how the vendor does their business, and understanding that upfront is a valuable thing to know.
Yes, it is a great example of the more you know, the more you know. Really diving into your suppliers and vendors. And software bills of materials are great. They answer some questions. They certainly don't answer all of these. Okay. My favorite principle, if I had to pick one, is planned resilience. And part of it is that the idea behind it is so intriguing. With planned resilience, we think about how we can turn what ifs into even ifs. So what if an attacker turned on all of the pumps on or off? What if the application vendor reported that they had been attacked by an adversary? What if the application just stopped working? What if the cloud vendor had ransomware? I want to think about how to turn these statements from, oh my gosh, challenges into, well, even if that happened, we have a plan. So here's an example for our system of planned resilience. If an attacker turned all of the pumps on or off, we use manual operations, we have our time delay relay, contact the vendor. We don't think that's going to hurt us very much, especially if it's one booster pump station or just a couple. What if the application vendor reported an attack? Well, we would return to manual operations, and we have a contract vehicle to ensure that we can staff that for up to 2 weeks. That will give the application vendor a chance to figure out what the impact to us of their attack might be and do any restoration that's needed. And we'll look with the cloud provider for a clean environment once all of that is done. What if the application stopped working? Well, kind of the same thing. We go to manual operations, and if this happened for longer than 2 weeks, we would need to arrange for emergency staffing and potentially find a new vendor. Same answers for what if the cloud provider had ransomware. The important thing in planned resilience is that we have a plan for how we can operate even in a degraded mode in the face of some sort of challenge. Jeremy?
Unmute. Likewise, so this is also my favorite principle. For me, and the way I think about cyber-informed engineering, it's planned resilience and the turning what ifs into even ifs that really embodies, again, for me, what we're really trying to accomplish. And and really, I mean, resonates with me going all the way back to, sort of when I really got into cybersecurity originally. I had the advantage at the University of Illinois working with some of the smartest power engineers in the country. And they only ever thought about resilience, right? If we had to take all digital control out of the power grid, could we still have power? And the answer is yes, because physics. And for me, that's what this is all about. It's how do we understand the system from its physics point of view so that we can take, even if our valve controls are compromised, you can't put too much chemical into the system, right? That's that pipe thing. And so it's this principle that really got me excited about cyber-informed engineering and kind of how I frame all of my thinking around CA.
Okay. Our next principle is engineering information control. This principle helps us think about how we manage knowledge about our system and keep it out of the wrong hands. And in this way, cybersecurity is really, really kind of ahead of the engineers. Often the cybersecurity team has very Byzantine processes for how they keep passwords hidden, how they keep specific system architecture information or networking diagrams hidden, but the engineers' information is all displayed. I remember seeing, as I did analysis work, many pictures of very happy executives standing in front of a new system as the ribbon got cut or the communications team was putting a picture in the newspaper. And as an analyst, I blew past the pictures of the people and started studying the systems. So what did they buy? What kind of system is that? Are there any configuration elements that I can discern from the way the picture looks? This is a great example of a lack of engineering information control. Additionally, if you've ever looked at a job description, often we put things in a job description so that we can signal the people that we want with the right knowledge, skills, and abilities to apply for our job. But when we are too specific or too descriptive, that will allow somebody to opt to understand what we need. This is many years ago, but a very critical government agency was putting out job listings saying that they needed people with Solaris skills. And they had other server technologies listed so that, again, as an analyst, I could say, oh, in your server, in the bowels of your server for your critical infrastructure, you're running Solaris. Now I can look at vulnerabilities to Solaris. I can look at attack mechanisms for Solaris. You've gotten me ahead of the game because I know what you're using. For engineers, this information also sometimes gets disseminated in contracting scenarios. When I'm contracting with a small business that's only so glad to do this work and very proud of it, they often will summarize the project on their website and put pictures and information and sometimes even diagrams and materials. So the core of engineering information control is making sure that the critical understanding of the engineering details of your system aren't accidentally published in a comms release or a job listing or a contract. For our system, we have some challenges. Municipal water activities are public record. The fact that we spent this money, how much we spent, and the fact that we spent it on a cloud upgrade, we are going to have to share. That will be a documented topic at some municipal meeting. And by the way, municipal meeting records tend to end up on the internet these days. So even though we think we only discussed it in our city, people around the world will be able to look at those minutes and see what we're doing. We have to share high-level information about this upgrade as public citizens. So we've got to decide what we should share and what we should withhold. What can we keep to ourselves? So the engineering team recommends to leadership that the specific vendor product name, and cloud vendor name be kept out of the record. If they want a juicy picture to put something around, we can create one that doesn't have the name of the vendor on it. Luckily, since this is a cloud system, we don't actually have to open the cabinet or show any devices. We can just show someone sitting in the central office operating the water system with someone else's water screen on it. We'll find something off the internet that we can pretend is our system's HMI. No one has to know it's not really our stuff. And that's how we can keep knowledge of the system out of the adversary's hands. Jeremy, I bet you have something on this one.
This is another one where kind of an aha moment for me. Specifically the job posting thing. Now, again, I come from the, my original background is really coming from that technology side of things as opposed to the engineering side of things. So we're all familiar with a number of years ago, there was a photograph taken of a control room in Hawaii, and somebody had a post-it note with a password on it. Kind of famous in the cybersecurity circles. But what I never even thought about was, well, how much information are you giving out in a job posting, right? You're looking for somebody with experience with Allen Bradley Relay or Allen Bradley PLCs. Now you've just told the whole world that you use Allen Bradley PLCs, and that's for what it's worth, right? That is actually a tremendous amount of information to have, because it helps you target and narrow the scope of your research if you're a bad guy.
Okay. We are on the 12th principle for cyber-informed engineering. This is both the starting and culminating principle and is the most important. And that is having a cybersecurity culture, even penetrating engineering. The question that we ask ourselves as we think about this principle is, how do I ensure that everyone performs their role aligned with our security goals? In this case, we have some really positive outcomes. For our particular cloud upgrade, the IT team didn't get to rule the show. They didn't get to say, hey, we found the system, we found the provider, finance is on board. Hey, engineering, you're just going to get this upgrade. Engineering was allowed to say, we have some concerns. We'd like to do a little bit of system analysis to figure out how we can contribute to the security of the system. That's a major thought. That's a major cultural shift for most organizations. As we think about cybersecurity culture, it's important for us to think about what functions in our organization are critical to our security and what we need them to know or do. In our case, we certainly mentioned HR. We don't want HR to put, you must have familiarity with XYZ cloud provider, because that's probably then going to enable an adversary to really come after us. We're going to want to talk to our comms team so that as they do press articles, they're careful about what they share and what they don't share. We may need to talk to our contracting team so that they're thinking about what information about our critical controls gets released. And we may need to think about talking with, our legal team. If we have an issue, a cyber attack that affects our water system, it may end up being a legal issue. And if we're doing an incident response, our legal team is going to need to be involved, and they're going to need to know what to say. We need to have conversations with everyone who has a role in any of the catastrophic consequences of the system so that they understand what solutions they bring to the table and how they can perform their role. Anything here?
No, this is another one that really resonates with me. Here at INL, and honestly all of the Battelle labs, we have this safe conduct of research, these safe conduct of research principles, and one of them is safety is everybody's responsibility, right? Everybody is responsible for the safe conduct of work that we do. And it's really this too, right? To cybersecurity isn't just the cybersecurity team's responsibility, it's everybody's responsibility. And with CIE, we're really reinforcing everybody, right? Because again, right, on that traditional cybersecurity IT side of things, you don't really think about what is engineering's role in cybersecurity. But if you're really building an organization-wide culture around positive cybersecurity principles, it has to include everybody, and that means engineering, and that means having those conversations and building those relationships across silos, breaking down silos entirely if you can, and realizing that everybody's on the same team. We're all trying to get to the same place, and do it safely and smartly and effectively.
Thank you. Okay, we have covered 12 principles and we're slightly over time. So I'm going to fulfill one promise that I had. I promised that I would talk to you about tools that you could use. You've looked across the breadth of what cyber-informed engineering is, talking about all 12 of its principles. But we have tools and capabilities that you can use to apply this in very specific endeavors. If you have an advanced distribution management system, we have a workbook so that you can think about how to apply cyber-informed engineering for that system. We've developed a specific system for microgrids and battery energy storage systems. So if you're looking to apply cyber-informed engineering for those, we have a way to make that much shorter and take less time. We have an implementation guide, and I think Andrew Ginter had some pictures of that. It has 1,178 questions that you can ask across the systems engineering lifecycle, and it may be helpful to look through those questions and see which ones resonate. That's a PDF, but if you'd like to take that tool and have it be downloadable, we also have a version of that. I put a list of links to these tools in the resources section of this particular conference. So click on the Zoom area for resources and you can pull down these links and start leveraging these tools. I'm going to skip through just a little bit. There's an image of the implementation guide. It has a lot of good information in it. At the very end, there's a case study that was written by Andrew Ort, who spoke to us on the first day, talking about a water team that applied these principles. I would welcome your questions and your thoughts as you begin to integrate cyber-informed engineering yourself. If you are a professor or a student, we also have curriculum materials that we would be delighted to share. If you'd like to get in touch with the cyber-informed engineering team, you can do that by emailing cie@inl.gov. Thank you, Prakash. I'll turn things back over to you for closeout.
Yeah, thank you, Jeremy and Ginter. This has been a fascinating discussion on CIE. I appreciate for you guys do a thorough information about CIE. I hope participants made use of this workshop, and Ginter and Jeremy will be available offline. If you want any questions on email, feel free to reach out to me or them. We're happy to coordinate and answer your questions. With that, I think the two-day workshop that is jointly hosted by INL and UND concludes here. And congratulations to the team, and thank you to my C2SR team as well who've been supportive of having all to make this a lively event. And also we will also have the recording available, will be made available and send it to you. Posted on our website later sometime. Okay. And yeah, that's it. So this concludes the session. Thank you, Ginter and Jeremy.
Thank you. Thanks to the university for all of the support, Tanzim and the other team members. We really appreciate it. You made it work beautifully.
And again, to reiterate, certificate of participation, certification with PDH is available only on request. And if you do so, then be prepared to take an assessment quiz with us, and then we'll make it available after you complete the assessment. Thank you, everyone.
Thank you.
Thank you. Bye.
Thank you.
Thank you.